quiet corner of the evening where you can settle in, let your shoulders soften and allow the day to drift a little further into the background. Tonight, you are joining a calm journey into one of the most hidden and surprising foundations of the universe, as we gently explore what quantum fields truly are and why they shape absolutely everything around you. Before we float too far into the deep, I would love to know where in the world you're listening from. It is always a soft and comforting thought to imagine this little community relaxing together from so many different places and time zones. And while you are here, if it's not too much to ask, a like and a subscribe would be deeply appreciated. To everyone who is already subscribed, thank you so much for supporting this peaceful space. If you would like to make sure you never miss the next calming upload, please tap the notifications bell so the next video quietly finds you. There is always a delicate balance with videos like this. Ideally, it lulls you gently towards sleep. But if it happens to be just a little too interesting and keeps you awake, at least you will drift off later with something delightful and mind-stretching lingering in your thoughts. So as you breathe a little slower, and as the room grows a little quieter, let your curiosity settle on one simple question that lies at the edge of everything you have ever known. If the world is not truly made of tiny solid particles, then what is it made of? For most of history, the universe seemed easy to picture. People imagined matter as countless tiny pieces, like grains of sand drifting through empty space and forming every object in existence. It was a simple picture, tidy and reassuring, and for a long time it worked well enough to explain the world. But as scientists looked closer, observing the behavior of light, electrons and atoms, the old picture began to crumble. Particles acted like waves. Waves acted like particles. Things appeared where they should not and vanished when no one was looking. The universe was whispering that something deeper was happening. This video will gently guide you through that deeper idea, the possibility that everything, from the smallest particle of light to the warmth of your breath, comes from invisible fields that fill all of space. These fields are not abstract mathematics or distant theories. They are the quiet foundation of reality, humming softly beneath everything you see and touch. In this introduction, think of yourself stepping slowly into a different way of understanding the world. There is no need to memorize anything or follow complex reasoning. The goal is simply to relax into a new perspective, to let the ideas wash over you like soft currents. As we move through this journey, layer by layer, you will hear how fields behave, how their vibrations become the things we call particles, and how these hidden structures give rise to the familiar world around you. You might find that the deeper we go, the less the universe feels like a machine made of parts, and the more it feels like a set of quiet landscapes, gently shifting, resonating, and unfolding. With each step, the picture becomes softer, stranger, and more beautiful. So allow yourself to slow down, to listen without pressure, and to follow the thread of curiosity as it leads downward into the quiet foundations of existence, where everything becomes a vibration in an invisible sea. For as long as people have wondered what the world is made of, the simplest answer has always felt the most comforting. Imagine taking any object around you and breaking it apart, then breaking the pieces into smaller pieces, and then continuing that process again and again. Eventually, common sense suggests you would end up with a final building block, a tiny bead that cannot be divided further. These imagined beads feel like they should explain everything. They are small, solid, and easy to picture. They sit neatly in the mind, the way marbles sit neatly in a bowl. It is an idea that has lived for thousands of years because it fits so naturally with everyday experience. When you drop something, you feel weight. When you tap a table, it pushes back. When you scoop sand through your fingers, you can imagine each grain as its own tiny piece of matter. A universe made of miniature solids seems obvious, reasonable, and reassuring. For centuries, scientists embraced this picture. It made sense that if an object is solid, then everything inside it must be solid as well. Even when the first atoms were proposed, they were imagined as tiny balls. Later, when atoms were found to contain even smaller components, people simply imagined smaller balls inside larger ones, like a set of nesting dolls with a hard little core at the centre. It was such a simple and tidy story that it became difficult to imagine any other. If everything feels solid and looks solid, then surely the world must be built from solid pieces. But the closer researchers looked, the more this simple picture began to drift away from reality. The first hints came from light itself. A beam of light could behave like a wave spreading gently across space. But under the right conditions, it also behaved like a hail of tiny particles. It was as if light refused to choose a single identity. This was confusing, but scientists managed to cope by adopting a kind of double vocabulary, treating light as waves for some problems and particles for others. It was not tidy, but it worked just well enough to postpone discomfort. Then electrons began to misbehave. If these were tiny beads, they should travel in straight lines like any small object. Instead, when researchers sent electrons through a narrow slit, the electrons produced patterns usually made by waves, not particles. It was as if each electron spread into a soft mist, drifted through space, slipped through multiple paths at once, and only later returned to the appearance of a single point when it hit a screen. The idea of a tiny solid electron rolling along like a marble no longer made any sense at all. Something stranger was happening beneath the surface. Imagine watching a raindrop fall into a still pond. You see ripples expanding in perfect circles. Now imagine that someone tells you the raindrop was not a raindrop at all, but a tiny bead that refused to follow any single path through the air. It behaved like a wave, yet somehow produced a clear landing point. That is the kind of puzzle electrons presented to researchers. They behaved like both a ripple and a bead, depending on how you looked at them. The confusion deepened when scientists tried to track the paths of particles more precisely. The moment they attempted to follow an electron on its journey, the electron would refuse to cooperate. Instead of offering a smooth trajectory like a pebble thrown across a field, the electron would sometimes disappear from one expected location and appear in another without taking any classical route in between. It was as if the particle refused to occupy a single definite position until it absolutely had to. It could smear itself out, drift in possibilities, and then suddenly commit to one outcome the moment it was observed. Photons behaved with equal stubbornness. When light was sent through two narrow openings, the resulting pattern looked exactly like the ripples you would expect from water waves, meeting and interfering with each other. But when scientists sent the photons one by one, giving each little packet of light its own moment, the exact same pattern slowly emerged. Each photon seemed to behave like a broad, gentle wave sweeping across both openings, yet still arrived as a single point of light on a screen. A tiny bead simply could not behave this way. Slowly, the old picture of a universe made of solid marbles began to fall apart. Scientists realized they were witnessing behaviors that no classical object could display. These were not tiny stones traveling through space. They were something else entirely, something capable of spreading out, interfering with itself, vanishing from one place and appearing in another without following any path in between. The old model was like trying to explain the behavior of the ocean by imagining it filled with glass beads. It was too rigid to capture the softness and fluidity of what was happening. There was an emotional moment in science when this discomfort became impossible to ignore. Physicists had to admit that the old story, the one that had seemed so tidy and sensible, no longer matched the world they were observing. The universe was behaving in ways no collection of miniature solid objects could manage. It was not enough to adjust the particle idea slightly, or add a few exceptions. Something fundamental about the picture itself needed to change. This realization created a feeling of standing at the edge of a cliff, looking out at a landscape that no one had mapped yet. The familiar explanation had dissolved, leaving behind a misty space filled with unanswered questions. If electrons were not little beads, what were they? If photons could ripple and interfere like waves, what exactly was waving? If particles could appear without following a defined path, what was guiding them? These questions lingered softly in the minds of scientists like distant echoes waiting for the right understanding to bring them into focus. The world was clearly made of something deeper, something that behaved in ways classical matter could not. The old picture had carried humanity a long way, but it had reached its limit. And so the question remained, quiet but persistent. If the things we call particles are not really tiny solid objects, then what are they made of? When you hear the word field, it might bring to mind an open stretch of grass or a quiet landscape under a wide sky. In physics, though, a field is something far more subtle. A field is a quantity that has a value at every point in space, something that quietly fills a region without needing to be seen. It is not an object or a collection of objects. It is more like an influence, a condition, a gentle presence that exists everywhere at once. To understand the idea, it helps to start with something familiar and slow the mind to a calm, curious pace. Imagine standing inside a cozy room in winter. Even if every part of the room feels warm, it is not exactly the same temperature everywhere. The air near a window might be slightly cooler. A corner catching sunlight might be a touch warmer. Every point in the space has a temperature associated with it, a little number describing how warm the air is right there. That temperature distribution is a field. You cannot pick it up or pour it into a cup, but it is there nonetheless, quietly assigning a value to each location. Or picture yourself outside on a gentle summer afternoon. You feel a soft breeze brushing across your skin. The wind is not uniform. In one spot it drifts lazily. In another it picks up strength, and just a few steps away it might swirl unexpectedly. At each location, the air has a specific motion. That movement, the speed and direction of the wind at every point, forms another kind of field. You may not see the wind with your eyes, but you can sense its presence, feel its behavior, and observe its shifting patterns. Even the pressure in the atmosphere forms a field. If you were to walk up a mountain, the air would become thinner. If you walked back down towards sea level, the pressure would rise again. Every location in the environment carries its own pressure, a value that helps weather systems form and guides the movement of clouds and storms. Pressure is another example of something that varies smoothly across space, a quiet pattern that influences the world without ever appearing as an object. These examples are simple, gentle ways of easing into the deeper idea. The fields that shape the universe behave in similar ways, though they are far more fundamental. They do not describe warmth, or wind, or pressure. They describe the underlying conditions that give rise to the forces and behaviors we see in nature. And unlike temperature or wind, which depend on nearby matter, the fundamental fields of physics exist whether or not anything else is present. They are woven into the fabric of space itself. Consider the gravitational field. No matter where you stand on Earth, you feel a gentle pull toward the ground. This pull is not caused by objects touching one another, nor does it travel from place to place like a thrown stone. Instead, the gravitational influence exists everywhere, shaping the motion of anything with mass. Walk a few steps in any direction, climb a hill, descend into a valley, and although the strength of the pull may change slightly, the field is always there, quietly guiding your motion. Or think about the electromagnetic field. Even when the room around you looks perfectly still, this field fills it completely. It is what allows a radio to pick up signals, a phone to receive messages, and sunlight to warm your skin. You might not be aware of it, but at every point in space, in front of you, behind you, above your head, the electromagnetic field has a specific condition, ready to ripple or react in response to the world. The important idea here is that fields are not like pebbles you can place on a table, or marbles you can line up in a row. They are more like invisible textures woven through space, each one carrying a quiet value that can change from point to point. They can be calm, as still as an undisturbed lake, or they can shift and ripple in response to activity around them. But they are always present, even in the quietest emptiness. To picture a field intuitively, imagine walking through a dark room with your hand gently outstretched. You cannot see anything, but you might feel subtle variations in temperature or a faint movement of air. You might sense the slight warmth drifting from a vent or the coolness near a window pane. In the same way, the universe is full of invisible variations, quiet properties that fill every corner. Fields are these hidden textures, mapping out conditions that exist whether or not we notice them. This idea may feel abstract at first, but it is surprisingly calming once it settles into place. Instead of imagining the universe as a scattering of isolated things, you can begin to imagine it as a series of smooth, continuous layers, like the gentle gradients of colour in a sunset or the soft shift of a breeze across a field of tall grass. Space is not empty. It is alive with structure, subtle though it may be. And while temperature, wind, and pressure fields are familiar and easy to sense, the more fundamental fields of nature are far deeper and more mysterious. They do not depend on weather or seasons. They do not vanish when you turn off the lights. They are simply part of how reality is arranged. They exist everywhere, quietly, continuously, and without interruption. They give space a personality, a set of conditions that make everything else possible. Even if you were to travel far from Earth and drift in the darkness between stars, these fields would still surround you. They do not fade when matter is scarce. They do not disappear when the environment becomes cold or silent. They are woven into the universe itself. So when physicists speak of fields, they are not describing objects. They are describing the quiet backdrop of existence, the subtle pattern that allows everything else to happen. It is a shift away from imagining the world as a collection of tiny beads and toward imagining it as a continuous landscape of invisible influences. Once this idea settles in your mind, it becomes easier to see how rich and textured the universe truly is, and it invites a gentle curiosity, the kind that asks not whether the world is made of tiny pieces, but rather what kinds of hidden patterns fill the space around us, waiting to be stirred into motion. When you picture a wave, You might think of ripples spreading across a pond after a pebble slips beneath the surface. The water itself is not travelling outward. It is simply moving up and down, passing the disturbance along in a gentle pattern. This idea translates beautifully to fields. Once you see a field as something that exists everywhere, something that has a value at each point in space, it becomes natural to imagine what happens when that value is nudged or disturbed. A field reacts the way a calm lake reacts to a falling drop. It carries the disturbance outward, letting it travel smoothly through space as a wave. This is one of the reasons the idea of fields began to shine a light on the strange behavior of electrons and photons. The wave patterns that confused early scientists were exactly what you would expect if the world were filled with fields. A disturbance in a field does not remain local. It spreads, it stretches out, and it forms patterns that can overlap, reinforce, or cancel one another, just as water waves do. Suddenly, wave behavior was no longer a mystery attached to objects that had no reason to behave that way. It was simply what fields do when they are stirred. Imagine a guitar string just after you pluck it. The entire length of the string begins to vibrate, not only the part where your finger touched. The vibration spreads, carrying energy and motion through the whole string in a pattern that repeats until the sound fades. Fields behave in a similar way. If you disturb a field in one small region, the effect travels outward, creating waves that move with elegance and simplicity. They can flow around obstacles, spread out through openings, or overlap with other waves, much like the patterns seen in those puzzling experiments with light and electrons. Even the ringing of a bell reveals the same idea. When you strike a bell, the whole surface responds. It vibrates in particular shapes, called modes, each one producing a distinct tone. Those vibrations travel through the air as sound waves and reach your ear. What you hear is not the movement of the bell itself, but the disturbance it sends outward. A field behaves in a way that is deeply reminiscent of this. A disturbance does not stay in one place. It resonates, it spreads, and it carries information along with it. But then there is the other side of the mystery, the part that made classical thinking crumble. When scientists measured light or electrons, they did not detect broad, smooth waves. They detected sharp, sudden events like tiny particles striking a screen at one specific point. It was as if the universe refused to reveal its wave nature directly. Instead, it arrived in tiny, concentrated packets, leaving crisp dots of light or distinct impact marks. At first, this seemed impossible to reconcile. How could something behave like a gentle wave and yet also appear as a precise localized point when measured? It was like watching a ripple drift across a pond, only to have it land on the far shore as a single bead of water, with no trace of the wave that carried it. The field picture offered a way through this confusion. Instead of imagining particles as little beads moving along definite paths, the field model treats them as disturbances in a field. These disturbances spread out like waves until the moment they interact with something else. And here is the key. Even though the wave spreads across space, the act of interaction, the moment when the wave deposits its energies is local. It is focused. It is like a whole ocean sending one drop of water to tap your finger. The wave can be wide, but the effect arrives in one place. This is why measurements always show what looks like a particle. You never detect the entire wave. You detect only the moment it leaves its mark, the moment the field transfers a packet of energy to whatever instrument is waiting. That packet is what scientists began to call a quantum. It is the smallest amount of energy a field can give during a single interaction. To the measuring device, it feels like a tiny object arriving with precision. But behind that simple arrival is a broad, gentle wave shape that carried the energy across space. In other words, the universe behaves like a wave until it has to make itself known. The spreading disturbance is always there, drifting quietly through space, but the moment of detection looks like a tiny particle arriving in one sharp instant. The contradiction that troubled early physicists melts away once you realize that both behaviors belong to the same underlying phenomenon. The wave belongs to the field. The particle-like event belongs to the interaction. To make sense of this, imagine tapping a long, stretched ribbon with your fingertip. The ripple created by the tap travels along the ribbon, spreading its energy. If you place a small bell somewhere on the ribbon, the ripple will eventually reach it and cause it to ring. The ringing of the bell is a single event at a single point. It does not tell you about the entire shape of the ripple that travelled along the ribbon, only that the ripple had enough energy to ring the bell when it passed that spot. Measurements in the quantum world work in a similar way. They reveal only the place where the wave decides to leave its energy behind, not the shape it took while travelling. This unified picture explains why light can create interference patterns while still arriving in discrete dots. The wave spreads out, passes through both openings, creates a pattern of peaks and valleys, and then, when it interacts with the screen, deposits its energy in one small location. The wave and the particle are not two separate things. They are two aspects of a single process, a disturbance moving through a field and then interacting in a focused way. For early scientists, this understanding was like watching a long confusing story finally click into place. The world no longer needed two contradictory descriptions. The wave behavior came from the field itself. The particle behavior came from how fields interact. The universe had not been switching identities or hiding its true nature. It had been behaving consistently the entire time. The confusion came from trying to describe waves as objects. Once you see the world through the lens of fields, the mystery softens. The strange experiments that once felt chaotic now feel natural. Waves arise because that is what fields do. Particles appear because energy is transferred in small, concentrated amounts. The two ideas weave together in a way that feels elegant, not contradictory. And so a quiet sense of clarity settles in. The universe begins to look less like a collection of stubborn little beads and more like a vast, resonant tapestry where disturbances flow smoothly until they choose a single point to touch. In this view, the puzzle that once seemed like an impossible contradiction becomes a gentle harmony, a simple consequence of living in a world shaped by fields. When you picture a vibration, you might imagine something that can vary smoothly. A guitar string can be plucked softly or firmly, with the vibration spreading along its length in endless gradations. A pond ripple can be small or large, gentle or energetic, drifting outward in a continuous flow. It would be natural to imagine that vibrations in a field behave in exactly the same free and flexible way. Yet at the deepest level of reality, nature shows an unexpected preference for order. The vibrations allowed within a field are not unlimited. They come only in specific, stable patterns, almost as though the universe prefers tidy melodies to chaotic noise. A helpful way to understand this begins with music. When you pluck a guitar string, you do not create just any shape of vibration. The string chooses from a set of allowed modes. These modes are the familiar harmonics that give instruments their character. The simplest mode is a single smooth curve stretching from one end of the string to the other. The next is a shape with a soft bend in the middle. Higher ones contain more bends, more nodes, more structure. Even if you strike the string randomly, it quickly settles into these preferred modes, vibrating in tidy, repeating patterns. Fields behave in a similar way. Although you might imagine a field producing every possible type of vibration, the universe permits only certain stable patterns. These patterns depend on the properties of the field itself. Some fields favor slow, rolling disturbances. Others support tighter, more energetic quivers. But in every case, the field chooses from a discrete set of vibrational behaviors. Unlike a pond ripple that could in principle take on countless shapes, a fundamental field resonates only in particular ways, the way a musical note rings with distinct tones. To picture this with even more softness, imagine stepping stones arranged across a quiet pond. If you want to cross, you cannot place your foot anywhere on the water. You must choose one stone or another. Each stone represents a stable place to land, and although there is water everywhere, your movement across it comes in distinct steps. Vibrations in a field behave in much the same spirit. The field might seem continuous, but the stable patterns it supports come in specific increments. These increments are the quanta, the individual packets of energy the field allows. This idea of quantization may sound abstract, but it shows up in the world around you all the time. When you see a bright color, when you feel the warmth of sunlight, when an atom emits a soft glow, each of these phenomena involves a field shifting from one allowed vibrational mode to another. The change does not happen gradually. It occurs in a tiny, sudden jump, like moving from one stepping stone to the next. This is what early physicists found so surprising. The universe does not let a field release or absorb just any amount of energy. It prefers clean, distinct amounts, as though counting each tiny transaction with meticulous care. And this brings us to the heart of the idea. These discrete vibrational modes are what we call particles. When a field vibrates in one particular stable way, we perceive that vibration as an electron, or a photon, or some other particle. The particle is not a little bead floating around. It is the smallest stable ripple the field can support. If the ripple becomes more energetic, the field moves to a higher vibrational step. If it loses energy, it drops to a lower one. But at every moment, the vibration fits one of the allowed patterns. It never hangs in between. This understanding gives a surprisingly elegant explanation for why particles always seem to appear in specific amounts. You cannot have half a photon any more than a guitar string can vibrate in half of a harmonic. The system either supports the full mode or it does not. Nature seems to enjoy this level of tidiness. It makes the behavior of matter wonderfully predictable once the underlying rules are understood. It can also make the world feel a little playful. Instead of imagining electrons as tiny spheres rolling around, you can imagine them as small, persistent ripples that refuse to be anything other than themselves. Each one is a field vibration asserting its identity, announcing in a quiet but unmistakable voice, "This is my mode, and I intend to keep it." It becomes almost humorous to think that the building blocks of matter are less like miniature stones and more like polite little waves insisting on being counted correctly. This view helps with many of the puzzles that confused early researchers. When light behaved as both a wave and a particle, it was not switching personalities or being indecisive. It was simply a field producing waves that came in neat, tidy packets. The wave aspect came from the spreading of the disturbance through the field. The particle aspect came from the fact that the field's energy is delivered in individual quanta. Both behaviors are natural once you understand that the field prefers distinct vibrational steps instead of a continuous range. Even the simplest atom begins to make more sense through this lens. The electrons within it cannot move in arbitrary patterns. They settle into stable modes of vibration around the nucleus, their shapes determined by what the electron field allows. When an electron changes its vibrational pattern, the atom emits or absorbs a quantum of light. This process feels less mysterious when you picture the atom as a miniature instrument producing clean, discrete notes. Quantization is the universe's way of keeping things orderly. Instead of allowing chaotic fluctuations, fields resonate in specific, well-defined patterns. These patterns give rise to the particles we observe, and once this idea takes root, it becomes surprisingly calming. The behavior of the smallest parts of nature is not chaotic at all. It is structured, patterned, and quietly musical. So when physicists talk about particles, they are not talking about little nuggets of matter. They're describing the allowed vibrations of fields, the stable harmonics of the cosmic instruments that fill all of space. A particle is simply a ripple that insists on being counted, a tiny vibration choosing one of the universe's permitted notes. It is a simple idea once it settles in your mind, and it brings a gentle sense of harmony to the strange world of the very small. Instead of imagining nature filled with objects that flicker in and out of existence, you can imagine it as a serene landscape of fields, each one humming with the possibility of vibration. When those vibrations settle into their allowed forms, the world you know begins to take shape, one quiet quantum step at a time. Imagine for a moment that everything around you is immersed in a vast and silent ocean. Not an ocean of water, but an ocean of something far more subtle, something that does not shimmer or splash, yet fills every corner of existence with quiet consistency. This ocean is the electromagnetic field. It is present in the air beside you, in the empty spaces between stars, and even in the silent vacuum that seems completely bare. No matter where you go in the universe, you are always swimming in it. This field is not something you can touch, and you cannot see it directly, but you experience its effects constantly. When sunlight warms your skin, when you turn on a lamp, when a phone receives a signal, when you look at the colours of a sunset, it is this field shifting, moving, or vibrating. The electromagnetic field is one of the most familiar fields in nature, even though it remains invisible. It is the gentle medium that carries light, warmth, and information from one place to another. To understand light in this picture, it helps to picture the field as a calm, wide ocean. When undisturbed, it sits in a quiet, uniform state, perfectly still. But the universe rarely leaves things untouched. A vibration can form in this ocean, a tiny, self-sustaining ripple that travels forward without needing anything to push it along. This travelling disturbance is what we call a photon. A photon is not a little bead darting through space. It is a ripple in the electromagnetic field, a pattern of motion that moves gracefully across the cosmos. Think about how a single drop of rain can send ripples across a pond. If the water is calm enough, those ripples will travel far from where they started, spreading energy outward in expanding circles. A photon behaves similarly, although its ripple is far more refined. Instead of spreading outward in a circle, it maintains a tight, self-contained wave as it moves forward. The field supports this motion, allowing the ripple to travel through space with remarkable steadiness. Now imagine those ripples coming in different rhythms. A slow ripple moves gently, taking its time. A faster ripple vibrates with more urgency. In the electromagnetic field, this rate of vibration is what your eyes interpret as colour. A slow, long wave is seen as red. A quicker wave becomes orange, then yellow, then green, and so on until the vibration becomes fast enough to appear violet. Your eyes are remarkable instruments, capable of detecting these subtle differences in vibration, translating them into the colours that fill your world. The intensity of the ripple also carries meaning. A faint, delicate vibration produces soft light. A stronger one produces bright light. When you step outside on a sunny morning, the warmth you feel on your skin and the brightness that surrounds you are simply the electromagnetic field vibrating with greater energy. The sun is stirring the field, sending countless ripples outward in every direction, and some of those ripples eventually reach Earth, where they gently brush against your skin or enter your eyes to create the colours of daylight. You can even think of wireless communication as a conversation carried by the electromagnetic field. When a device sends a signal, it creates patterned disturbances in the field. These patterns travel outward like organised ripples, eventually being picked up by a receiver that understands the fluctuating vibration and translates it into sound, image, or information. It is as though the field allows distant objects to whisper to each other across empty space. Even something as ordinary as the gentle glow of a lamp is simply the electromagnetic field being stirred by an electric current. The electrons drifting inside the bulb set the field into motion, creating ripples that spread outward and fill the room with light. You see the lamp as a bright object, but what you are truly seeing is the field responding to the motion of charges, transforming their activity into waves that your eyes can perceive. And because this field fills all of space, light can travel extraordinary distances without needing anything to carry it. A ripple can move through the vacuum between stars just as easily as it travels through the air beside you. When you look up on a clear night and see starlight, you are witnessing ripples that have crossed unimaginable stretches of darkness, sometimes travelling for thousands of years. They left their stars long before anyone on Earth existed, and they continued on, unbothered and unchanged, until they finally reached your eyes. It is a peaceful thought. The universe is always sending gentle ripples through this field, and your eyes are sensitive enough to catch them. This picture also helps explain why light behaves with such elegance. Because it is a ripple in a field, light does not need a physical path. It is guided entirely by the field's properties. When light bends around a corner through a narrow opening, it is simply the wave spreading in response to constraints in the space. When two beams of light overlap, their ripples can combine, producing patterns that resemble the interference of water waves. The behavior can seem puzzling when you imagine light as tiny pellets flying around, but it becomes perfectly natural when you imagine it as a vibration in a continuous medium. The field is also patient. It will support ripples of almost any wavelength, from long lazy ones used for radio communication to short intense ones that appear as ultraviolet or even X-rays. Each type of ripple fits easily into the field structure, allowing an enormous range of behaviors. The colourful world you see is only a small part of this spectrum. Beyond the edge of what your eyes can detect lie ripples too slow or too fast for human senses, yet still moving through the field with quiet precision. There is something deeply soothing about this view. Instead of imagining photons as tiny frantic particles darting everywhere, you can imagine the universe filled with subtle vibrations. Light becomes a gentle ripple in an ocean that extends infinitely in all directions. Warmth becomes the tremble of that same field stirring against your skin. Colours become the rhythm of the ripple, each one a different note played on the cosmic instrument that surrounds us. And perhaps there is a small comfort in knowing that even in the deepest darkness, the electromagnetic field is still there, ready to carry any ripple sent through it, Space is rarely truly empty. It is filled with potential, a canvas for light to drift across. When you picture a photon travelling from a distant star on a quiet night, you can imagine a small ripple moving steadily across a vast silent sea, unhurried and unbroken, a tiny wave that has journeyed for countless years just to reach you. In this gentle view of the world, light is not a thing. It is a movement, a vibration, a moment of the field expressing itself. And once you see it this way, the universe begins to feel less mechanical and far more alive, as though space itself is capable of singing in colours. If you could zoom in far enough on the space around you, past grains of dust, past the tiniest specks of matter, deep into the territory where atoms begin to appear, you would find something surprisingly calm. Beneath the busy world of molecules and motion, the electron field rests like a smooth and uniform background, steady and ever-present. It does not come and go. It does not flicker or pulse unless something disturbs it. It is simply there, quietly filling all of space in an unbroken sweep. And within this field, the familiar electrons that shape every atom are not little objects darting around, but the smallest stable ripples the field can support. These ripples are gentle, minimal disturbances, like small rings on the surface of a still lake after a single drop of water falls. When the electron field is excited in just the right way, a tiny, well-defined ripple appears. This ripple is what we call an electron. It is not a bead or a speck, even though we often draw it that way. It is more like a precise vibration that refuses to fade as long as it remains in a stable state. The electron field supports these ripples naturally, allowing them to persist, move, respond to forces, and interact with other fields. This becomes especially important when we begin to think about atoms. The classical picture imagines electrons circling the nucleus like miniature planets orbiting a tiny star. It is a charming image, and for many years it was the best way anyone had to imagine atomic structure. But a planet follows a clear, predictable path. An electron does not. If electrons truly behave like planets, their curved paths would gradually drain energy, causing them to spiral inward and crash into the nucleus in an instant. Atoms would collapse the moment they formed, which would be terribly inconvenient for anyone hoping to exist. Instead, electrons behave like standing patterns in the electron field. Picture a guitar string again, but imagine that instead of vibrating along a thin thread of metal, the vibration occurs in three-dimensional space. The electron field around a nucleus supports standing modes, patterns of vibration that can repeat without fading. These patterns are not flat or circular. They form cloud-like shapes, soft and fuzzy distributions where the ripple tends to appear. The electron is not somewhere in the cloud. The electron is the cloud. It is the shape of the vibration itself. This idea is gentle once it settles into your thoughts. Instead of imagining tiny objects zipping around in frantic motion, you can imagine a field adopting a shape. Each standing pattern has its own unique structure and energy, and each one can hold exactly one ripple in a stable way. The lowest energy pattern hugs closest to the nucleus. Higher energy patterns spread a little farther out, forming distinct layers. These layers are what we usually call shells. They give the atom its size and help determine its behavior. Atoms owe their stability to these allowed patterns. The electron field refuses to support vibrations that do not fit its natural modes. Just as a guitar string cannot settle into a weird, uneven wobble that does not match one of its harmonics, the electron field cannot maintain a ripple that does not fit one of its permitted shapes. This constraint keeps electrons from drifting too close to the nucleus or wandering too far away. They settle into the shapes allowed by the field, and those shapes define the atom. This is why atoms have size. Even though most of an atom is empty space, the electron field creates a region where the standing pattern of the ripple must exist. The atom extends out to where the electron field's lowest energy shape sits. The size of this pattern does not shrink indefinitely. It is defined by the balance between the nucleus pulling inward and the field enforcing its stable shape. The result is a softly bounded space, a region where the electron field hums in one of its permitted arrangements. The shapes of these standing patterns are surprisingly beautiful. Some are round and smooth, with no preferred direction. Others stretch into gentle lobes, almost like petals or clouds drifting in 3 dimensions. These shapes arise naturally from the mathematics of the field, but you do not need the mathematics to appreciate their elegance. They are the universe's way of organizing the vibration of the electron field around a positive charge. Each shape is a possibility, a quiet mode waiting to be filled. Because electrons settle into these shapes with almost stubborn consistency, atoms behave predictably. The electron field determines how much space an atom occupies, how strongly it holds its electrons, and how likely it is to interact with other atoms. The stability of matter, the reliability that lets your chair remain a chair and your cup remain a cup, stems from the electron field insisting on these stable, unchanging patterns. It does not allow chaos. It does not allow wobbling or drifting. It maintains structure with remarkable discipline. There is a peacefulness in this picture. Electrons are not racing around in dizzying circles. They are resting in gentle, continuous vibrations. They occupy shapes rather than paths. They fill space in smooth gradients rather than sharp dots. The atom becomes less like a miniature solar system and more like a quiet arrangement of field patterns, each one settled into the configuration that requires the least effort. And yet, this calmness is what gives the world its complexity. The fact that the electron field supports different patterns is what allows atoms to vary, and this variation is what makes chemistry possible. But for now, the essential idea is that the electron field creates dependable shape and size. It gives the atom the equivalent of a soft outline and a stable internal arrangement. Without this field and its insistence on standing patterns, matter would be an unpredictable mess, unable to form the familiar structures you rely on every day. So when you imagine an atom from now on, try letting go of the old picture of tiny marbles darting around a central core. Instead, imagine a calm, uniform field supporting a set of quiet vibrations, each pattern fitting perfectly into the space around the nucleus, each one holding its place with gentle persistence. The atom becomes a softly defined region of harmony, built not from orbiting objects but from the steady, unbroken behavior of the electron field itself. Deep inside every familiar piece of matter, far beneath the scale of atoms and the gentle shapes of electron fields, lies a region where the universe behaves with far more intensity. It is a place where fields intertwine tightly, where vibrations refuse to drift apart, and where nature holds its deepest structures together with astonishing strength. This is the world of quark fields and the strong interaction, a realm so hidden that for most of history no one suspected it existed, yet it is the foundation that allows everything else to stand. To understand this realm, it helps to begin quietly. Just as electrons arise as ripples in the electron field, quarks appear as ripples in their own set of fields. There are several types of quark fields, each capable of supporting its own stable disturbances. These ripples are far smaller and far more energetic than the ones associated with electrons. They live inside the heart of matter, deep within the atomic nucleus, in a place where space feels tight, and where the rules of everyday experience fade into something much more dramatic. A single proton or neutron is not a solid bead. It is a shimmering bouquet of these quark ripples, bound together so tightly that they behave as one unified structure. 3 minimal quark excitations settle into a stable arrangement, supported and confined by the powerful field that surrounds them. You can picture this field as a kind of invisible glue, but glue is far too gentle and passive to capture the behavior here. The strong field does not merely hold quarks together, it binds them with a fierce determination that grows stronger the more you try to pull things apart. This behavior is known as confinement, and it is one of the most striking features of the strong field. Imagine a stretchy fabric, thick and stubborn, with 3 small marbles pressed into it. If you try to pull one marble away, the fabric stretches and tightens, resisting more and more as the marble moves. Pull harder, and the fabric strains. But rather than letting the marble escape, it becomes increasingly difficult to separate. The fabric does not weaken as it stretches. It pulls back with even greater force. The strong field behaves in much the same spirit. When quarks sit close together, the field is calm and stable, but if you try to separate them, the field becomes tense and energetic, resisting the separation with surprising strength. The more they are pulled, the more the field pushes back. And if you somehow manage to pull with enough force, the energy required to stretch the field would grow so large that the field itself would create new quark ripples rather than allowing any quark to escape alone. Nature would rather make something new than let a quark wander off by itself. This is why quarks are never found individually, only as part of larger structures. Inside a proton or neutron, this constant pull creates a kind of internal storm. The quark ripples jostle and interact, dancing within the confines of the strong field. They exchange energy with the field, which pushes back with unyielding pressure, maintaining the trio in a tight humming configuration. It is a world of motion, of fluctuating energy, of deep and restless activity, all hidden beneath the calm appearance of everyday matter. This storm is not chaotic, though. It is contained, disciplined by the strong field, which keeps the entire system stable. The quark ripples cannot drift far from their partners because the field won't let them. They settle into an arrangement that balances their motion with the field's tension, forming a particle that behaves as a single, unified entity. When you see a proton or neutron in a diagram, it is usually drawn as a neat sphere. But inside that sphere is something far more dynamic. Quark vibrations swirling beneath a force that refuses to loosen its grip. This confinement gives matter much of its solidity. The strong field ensures that the heart of each atom, the nucleus, remains compact and durable. Without this field, the immense energy within the nucleus would tear it apart instantly. The protons within it carry positive charge, which normally would push them away from each other with force. But the strong field overwhelms that push. It binds the quark structures so tightly that the nucleus can endure despite those repulsive interactions. It is like having a group of magnets trying to fly apart, all wrapped in a band of thick, unbreakable elastic that pulls them together no matter how hard they try to separate. This interplay of forces creates a delicate balance at the core of matter. The strong field is unimaginably powerful at short distances, but fades quickly beyond the edges of the nucleus. Outside that region, the world feels calm and classical again. Inside it, The field is coiled with tension, constantly working to keep the quark ripples locked into their stable configurations. The atomic nucleus may appear small and simple, but it is held together by one of the most intense interactions in the universe. It is astonishing to think that everything you see, touch, or hold owes its structure to this hidden realm of activity. The chair you sit on, the air you breathe, the bones in your body, each one is built on a foundation of quark fields humming quietly within their strong binding. Without this field's unyielding grip, matter would not simply be different, it would not exist. There would be no stable particles to form atoms, no atoms to form substances, and no substances to form the familiar world. There is quiet poetry in knowing that beneath the surface of everything lies a storm that never quite calms, a storm held in perfect balance by one of nature's most determined forces. The strong field ensures that the building blocks of matter remain whole, cohesion born from unrelenting tension. It is a force that never falters, never loosens, and never allows its quarks to wander off into the void. In the gentleness of everyday experience, nothing hints at this deep internal struggle. A stone feels solid, a cup feels smooth, a leaf feels fragile. Yet beneath these simple sensations is a world of vibrating quark ripples locked in place by a field that behaves as though it has sworn an oath never to let go. It is a quiet truth, tucked away at the smallest scales, where the universe holds its breath and keeps its secrets wrapped in strength. When you imagine the interior of matter now, try to picture not a static core but a restless landscape, full of motion and energy, unified by a field strong enough to tame it. That constant invisible storm is part of everything you have ever known, a reminder that even the calmest world is built upon layers of astonishing activity. In the familiar world of everyday motion, a force often feels like a push or a pull. You push a door and it swings open. You pull a drawer and it slides toward you. These actions seem direct and mechanical, like one object pressing onto another. But at the deepest level of nature, forces do not behave like that at all. Nothing truly pushes, nothing truly collides. Instead, forces arise through communication, soft, continuous interactions between fields that overlap and respond to one another. To ease into this idea, picture two calm ponds resting beside each other, their waters almost touching. If a stone falls into one pond, spreading ripples across its surface, those ripples eventually reach the boundary between the ponds. When they do, the disturbance does not simply stop. It influences the water of the second pond, nudging it, inviting it to ripple in response. The two bodies of water do not collide, yet the disturbance spreads from one to the other through gentle interaction. This is closer to how forces work in the language of fields. Every field extends throughout space. Even when nothing dramatic is happening, they're all layered and overlapping, like transparent oceans occupying the same region. When a ripple forms in one field, nearby fields notice. They adjust, shift, or respond based on the disturbance. This adjustment is what we interpret as a force. It is not an object pushing another. It is a field changing shape, and another field responding to that change. Imagine a breeze drifting across a meadow and meeting another breeze coming from the opposite direction. The two do not collide the way marbles collide. Instead, their motions blend smoothly. They influence each other, altering their paths and slowing or strengthening each other. The air does not need to push in a violent or abrupt way. It simply adjusts to the currents surrounding it. Fields behave with this same softness. They notice each other's presence and behave accordingly. Consider a simple example: the electromagnetic field surrounding a charged particle. If that charge sits quietly, the field around it has a stable configuration. It does not push or pull anything by itself. But if another charge enters the scene, that second charge disturbs the electromagnetic field in its own way. The two disturbances blend, creating a new configuration that influences both charges. Each one reacts to the combined shape of the field around it. Neither charge needs to touch the other. They simply respond to the changing landscape of the field that connects them. This view of forces removes the need for tiny invisible hands pushing things around, or miniature marbles bouncing off one another. Instead, the universe acts like a continuous fabric. When one area of the fabric is pulled, stretched, or rippled, other areas subtly adjust. Everything responds to changes in the fields it shares space with. What feels like a direct push is actually the result of one field shaping another. Different fields have different sensitivities. Some respond strongly to disturbances, others barely react, and still others do not interact at all. This variation determines the strength of the forces we experience. The electromagnetic field is particularly responsive. A small disturbance can create a noticeable effect over long distances, which is why charges attract and repel one another with such clarity. The strong field is far more intense but acts only at extremely short ranges, creating immense force within atomic nuclei, but little influence beyond that tiny domain. The gravitational field responds more gently than any other, shifting subtly in the presence of mass and influencing objects from great distances with a steady, quiet pull. Even with these differences, the principle remains the same. Fields communicate through how they change. A ripple in one field creates a shift in the patterns of another. The fields adjust until they reach a configuration that satisfies all of them simultaneously. The result is what we experience as a force. To make this more intuitive, imagine standing on a soft mattress. When you shift your weight, the mattress dips beneath you. If another person stands nearby, they feel the slope you create. If they move, you feel the change they introduce. Neither person is pushing the other directly. Instead, each one is responding to changes in the shared surface. Replace the mattress with space itself, and replace the dips with field disturbances, and you begin to see how forces can arise from geometry and response rather than contact. There is a calming elegance to this picture. Instead of thinking of the universe as a place full of collisions and impacts, you can imagine it as a realm where everything communicates through subtle changes. When an object accelerates, it is not because something shoved it abruptly. It accelerates because the field around it changed shape, guiding its motion in a smooth, continuous way. Forces become expressions of harmony rather than violence, adjustments instead of impacts. Even everyday experiences can be viewed through this lens. When a magnet pulls a piece of metal, nothing reaches out to grab it. The magnetic field shifts in such a way that the metal feels a new configuration guiding it toward the magnet. When your hair stands on end from static electricity, it is not because of tiny particles pushing each strand upward, but because the local field has changed, encouraging each hair to move away from its neighbors. This perspective also reveals why fields are essential for understanding nature. Without them, forces would require objects to interact through direct contact, which becomes impossible at the scales where particles seem to appear and vanish without paths. Fields remove the need for physical closeness. They allow things to influence one another across distance through patterns rather than collisions. Perhaps the softest and most comforting part of this picture is that nothing is ever truly isolated. Every ripple, Every motion, every disturbance speaks to the fields around it. Everything communicates continuously, almost effortlessly. Even in the quietest void, fields remain present, ready to respond to the slightest change. There is a sense of connection woven into the structure of reality, not the kind of connection that binds things rigidly together, but one that lets each piece of existence feel the presence of the others. In this way, forces are not abrupt events. They are conversations. They are the universe responding to itself. And once you see them like this, the idea of a push or a pull becomes just a shadow of something much more elegant. The real truth is that fields shape the movement of everything by gently adjusting the world around them, creating a choreography where nothing ever truly collides and everything continually listens. It is a soft and quiet language, spoken in ripples and responses, shaping the motion of the universe with a kind of effortless grace. If you were to imagine empty space, you might picture a vast, silent stillness, a perfect nothingness, a canvas with no marks upon it. It is an intuitive idea, and a comforting one, because emptiness feels simple. But in the world of fields, even the quietest space is not truly empty. The vacuum is not a barren void. It is a restless foundation, a place where every field in the universe settles into its calmest possible state, yet never becomes completely still. Each field has what physicists call a lowest energy state, a kind of gentle resting position. But unlike a stone lying motionless on the ground, a field cannot settle into absolute stillness. Even in its calmest configuration, it quivers ever so slightly. These tiny motions are the field's quiet breathing, soft, nearly imperceptible fluctuations that drift in and out of existence. They do not build into anything dramatic. They do not erupt into storms or flashes. They simply rise and fade with a delicacy that borders on silence. You can imagine this subtle motion by picturing a sheet of fabric stretched tightly across a frame. Even when no one touches it, a faint tension remains. It might tremble in response to the smallest change in the air or shift gently when temperature alters the fibres. The surface appears still, but at a deeper level it is always poised, always carrying a hint of movement. Space behaves in much the same way. Every point in the vacuum is threaded through with fields that never fully relax, each one carrying just enough fluctuation to remind you that emptiness is not the absence of everything, but the presence of something remarkably subtle. These tiny quivers are sometimes imagined as small ripples rising and falling like breaths. A soft oscillation here, a fleeting vibration there. Nothing sustained, nothing dramatic, just a continuous hum beneath existence. If you could shrink yourself down to an impossibly small scale and listen closely enough, you might feel the faintest whisper of these fluctuations, like the quiet ticking of a clock far away in another room. They give space a texture, a gentle background rhythm that supports everything else. This restless foundation is essential for the stability of the universe. Without it, fields would be too rigid, too brittle, unable to respond to the world around them. The vacuum's quiet activity creates a kind of flexibility, allowing fields to shift smoothly when something disturbs them. It is like the difference between walking on firmly packed earth and walking on ground that has just the slightest softness to it. The softness does not announce itself, but it changes the way everything moves. Even in complete darkness, even in the silent stretch between distant stars, this gentle motion persists. There is no such thing as a place where fields vanish entirely. They extend everywhere, filling all of space, and their lowest energy state reaches into even the loneliest places in the universe. It is comforting in a way to know that space itself is never truly absent. It is always carrying a faint undercurrent of motion, a quiet reminder that the universe is alive with possibility even when nothing seems to be happening. Scientists sometimes call this subtle motion zero-point energy, a name that hints at the idea that even at the point where energy should be zero, something remains. But you do not need to think of it in technical terms. It is enough to picture the vacuum as a vast ocean at dawn, perfectly calm on the surface but carrying invisible currents deep below. These currents do not disturb the water above, but they give the ocean its character and depth. The vacuum behaves similarly, holding within it an undercurrent that never fully disappears. This restless space also helps explain why fields respond so quickly when disturbed. If a field were perfectly still, it would take effort to set it into motion. But because fields are already gently trembling, even the slightest nudge can send a ripple moving across space. The vacuum is not an obstacle to waves. It is a medium that is always just a breath away from motion. This makes the behavior of light, electrons and other field excitations remarkably smooth. They glide through this restless sea with ease, supported by the quiet activity beneath them. These fluctuations are not chaotic. They are more like faint echoes, rippling in and out with no lasting impact. They do not accumulate or grow. They simply appear and vanish in patterns that average out to a calm whole. If you stood in a forest on a perfectly still day, you might sense the tiniest shivers of movement in the leaves. Not wind exactly, but the forest responding to countless subtle influences. The vacuum is a bit like that. It appears tranquil from a distance, but up close it carries a living stillness, a stillness with texture. There is a gentle humour in the idea that the emptiest places in the universe are quietly active. If space could speak, it might say, "I may look empty, but I am doing my best work right now." Because without the vacuum's tiny fluctuations, fields could not settle into stable states. Particles would not form the same way. Light would not behave with its familiar grace. Even atoms might struggle to exist as we know them. The vacuum's subtle motion underpins the fabric of reality, offering a foundation that is lively enough to support change yet calm enough to vanish beneath notice. When you look up at the night sky and see a dark expanse between stars, you're not looking at nothing. You're looking at a vast field-filled canvas, a place where countless tiny ripples rise and fade in silence. You are looking at a region that is gently alive with motion, even though no eye can see it. And although this activity is delicate, it is everywhere, shaping the world in ways both hidden and essential. Understanding this brings a kind of peace. The vacuum is not a cold void. It is a quiet companion to everything that exists, offering a stable yet restless foundation that allows the universe to unfold with grace. And once you know this, the silence of space feels different. It feels full, textured, and softly breathing. A calm hum beneath all things, steady and unbroken. If you imagine all of space as a quiet, invisible landscape, you might picture some regions filled with fields and others left perfectly empty. Yet one field refuses to leave any space unoccupied. It stretches everywhere, filling the universe as uniformly as darkness fills a moonless night. This is the Higgs field, a subtle presence woven through every corner of existence. It does not shimmer or sway in any obvious way, and you would never know it was there by simply looking around. But every particle that moves through space must interact with it, and in doing so reveals one of the calmest and most important truths about the nature of matter. To picture the Higgs field, think of a thin mist resting gently over a landscape, the kind of mist that clings to everything but is easy to overlook. You walk through it without noticing, yet it is always there, brushing softly against your skin. The Higgs field behaves with that same quiet persistence. It fills all of space, not just near stars or planets, not just in crowded regions, but everywhere, from the smallest corner of your room to the deep, expansive darkness between galaxies. It never thins, never vanishes, never takes a break. It is the closest thing the universe has to a perfectly consistent background presence. When a particle moves through this field, it experiences a kind of gentle resistance. Not resistance in the sense of friction or rubbing, but a deeper, more fundamental kind of reluctance. The particle must interact with the Higgs field as it moves, and the strength of that interaction determines how much the particle resists changes in motion. This resistance is what we call mass. It is not something stuffed inside a particle like material in a backpack. It is the way a particle negotiates with the Higgs field as it moves through space. To imagine this more clearly, picture yourself walking through a shallow pool of water. When you try to move quickly, the water gently pulls against you. When you slow down, the pull weakens. You're still free to move, but the water makes it harder for you to change your speed. That reluctance feels similar to what mass represents. The water is not adding weight to your body. It is simply resisting your attempts to accelerate or decelerate. The Higgs field behaves in a similar way for particles. The more strongly a particle interacts with the field, the more the field resists its motion, and the more mass the particle appears to have. For particles that interact only weakly with the Higgs field, moving is easy. They glide through space with almost no resistance. This is why particles of light, which barely interact with the Higgs field at all, move effortlessly at the cosmic speed limit. For particles that interact strongly, the Higgs field pushes back more. Their motion feels heavier, more deliberate. They resist acceleration, just as you resist a sudden sprint through waist-deep water. The idea that mass comes not from what a particle is, but from how it moves through a field, is one of the most surprising discoveries in modern physics. It shifts the picture of matter from something solid and self-contained to something relational, something dependent on the environment that surrounds it. The Higgs field is that environment, shaping the behavior of particles simply by being everywhere. This explanation also reveals why different particles have different masses. Each type of particle has its own relationship with the Higgs field. Some feel only a faint tug, others feel a firm and steady drag. Each one negotiates its movement with the field in its own way, like travellers walking through mist of varying thickness. A little mist barely slows you down. A dense fog clings to you with more determination. The Higgs field treats each particle differently, and the universe expresses that difference as mass. This gentle process is far removed from the messy, mechanical explanations people once imagined. Mass is not a substance. It is not a filling or a material property. It is a behavior, a response. It describes how much a particle hesitates when the universe tries to change its motion. And that hesitation comes from the ever-present Higgs field, offering a quiet, uniform resistance everywhere. You might wonder why this field is so important if it is so subtle. The answer lies in stability. Without the Higgs field, particles would all move at the same effortless speed, racing endlessly without the distinctions that give matter its structure. Electrons would not settle into the patterns that form atoms. quarks would not combine into protons and neutrons in the familiar way. Everything would behave like light, slipping through space without slowing or stopping. The universe would be a restless sea without the ability to gather itself into stars, planets, or anything that resembles matter. By giving particles mass, the Higgs field allows them to slow, to settle, to bind together. It grants them the capacity to stay near one another long enough to form the structures that fill the cosmos. It gives weight to your body, solidity to the ground beneath your feet, and permanence to the objects around you. Mass is what allows matter to linger instead of dissipating. It is what gives form to the world and makes the universe feel grounded, balanced, and familiar. There is a peaceful charm in imagining a field that stabilizes everything by simply existing. The Higgs field does not push or pull. It does not rumble or roar. It quietly offers resistance to movement, shaping the behavior of every particle that passes through it. It is like a steady hand resting beneath the universe, keeping everything from spinning off into restless chaos. You can think of the Higgs field as a silent partner to all motion, always there, always participating, always ensuring that particles behave with the steadiness needed for matter to exist. The world feels solid because particles interact with this field in just the right way. The universe feels structured because the Higgs field slows the wildest tendencies of particles, allowing them to gather, combine, and create the richness we see around us. Even though it is invisible and undetectable to our senses, the Higgs field gives the universe its character. It provides the quiet reluctance that makes mass possible, and, through that, shapes the rhythm of everything that moves. If the Higgs field were ever to disappear, the universe would unravel into light, unable to hold itself together. But it does not disappear. It is woven into the fabric of space, steady and uniform, a constant companion to every particle that drifts through the cosmos. Once you understand this, mass no longer feels like a mysterious property buried inside matter. It feels like a calm, continuous conversation with a field that fills all of space. It is the gentle drag that allows the universe to take shape, the quiet origin of solidity, and one of the most subtle yet essential gifts of the fields that thread through existence. Inside every atom lies a quiet arrangement of fields that have settled into harmony. Nothing inside an atom behaves like a miniature machine with gears and tracks. Nothing obeys the tidy picture of tiny spheres orbiting a core like planets around a star. Instead, an atom is a small island of order formed from overlapping field patterns, each one shaping the behavior of the others until everything finds a stable configuration. Once the electron field, the quark fields, and the Higgs field are understood on their own, the structure of an atom becomes not just understandable, but almost soothing, as though nature itself prefers calm, repeating patterns whenever possible. At the center of an atom sits the nucleus, a compact arrangement of field excitations held together by the strong interaction. Within that nucleus, the quark fields combine to create protons and neutrons, and the proton patterns in particular carry a positive electric influence. This influence is not a physical object or a beam of energy, but a gentle shaping of the electromagnetic field around the proton. You can imagine each proton creating a soft, positive well in the surrounding field, almost like a dip in a flexible fabric. This positive region doesn't reach out with arms or hooks. It simply changes the shape of space in a way that invites negatively charged excitations to settle nearby. Those negatively charged excitations are the ripples of the electron field. When left alone, the electron field prefers to remain in a smooth, uniform state. but in the presence of a proton's positive influence, the field finds new stable patterns it can adopt. These patterns are the standing shapes that form around the nucleus, the same shapes that earlier chapters described as cloud-like and gentle, rather than sharply defined. The electron field notices the attractive pull of the proton and settles into configurations that balance that pull with the natural structure of the field itself. This balance is the reason atoms form. If the electron field only felt attraction, it would collapse directly into the nucleus. If it only resisted change, it would drift away forever. But the combination of the electromagnetic influence from the proton and the standing wave nature of the electron field creates a place of compromise. The result is a stable, softly defined region where the electron field settles into a quiet vibrational pattern. This shape is what we interpret as an electron occupying an atomic orbital. These shapes are not random. Each one is a specific arrangement that satisfies the field's requirements, similar to the allowed harmonics on a guitar string. The lowest energy shape is the simplest, like the fundamental note on an instrument. Higher shapes become more elaborate, forming lobes or rings or layered structures as the field adopts increasingly complex standing modes. These are the atomic energy levels, each one a harmonic of the electron field shaped by the presence of the nucleus. When scientists talk about an electron moving to a higher energy level, they are not describing a small bead climbing a ladder. They are describing the electron field shifting its vibrational pattern to a more energetic mode. When it falls back down, the field relaxes into a simpler configuration, and that relaxation releases a tiny packet of energy, often as light. In this way, atomic transitions behave like musical chords changing from one harmony to another, each shift creating a clear, distinct tone. These energy levels are the quiet architecture of atoms. They set the size of the atom, because only certain standing patterns are allowed. They set the behavior of the atom, because the shape of the electron field determines how the atom interacts with others. They even determine the colors that substances emit or absorb, because each transition between patterns corresponds to a particular note on nature's spectrum. What is most beautiful about this picture is how naturally everything fits together once the idea of fields is in place. Atoms do not collapse because the electron field cannot adopt a pattern smaller than its lowest energy state. That state represents the gentlest, calmest vibrational mode possible around a proton. Going lower than that would require the field to violate its own structure. It simply cannot. The same softness that creates the standing patterns also prevents collapse. Atoms also do not fly apart because the proton's influence holds the electron field's standing pattern in place. Removing that influence would require adding energy, which the system naturally resists. The atom, therefore, becomes a stable island of balance, shaped entirely by the interplay of fields settling into their preferred configurations. Imagine a tiny oasis floating in the vast sea of the universe, a place where the electron field has curled into elegant patterns around a nucleus, each layer humming in its own quiet mode. The atom becomes a peaceful structure, one that forms not through forceful interactions but through gentle arrangements. It persists because the fields naturally choose these shapes whenever the conditions allow them. On a much larger scale, the universe is filled with these islands of order. Each one behaves according to the same principle, fields influencing fields until everything settles into stable, repeating forms. The proton patterns provide the positive centers, the electron field surrounds them with harmonic shapes, and the Higgs field gives each ripple the mass needed to behave with steadiness. When all these influences blend together, atoms emerge not as mechanical objects but as quiet arrangements of field patterns. This is why the world feels stable. This is why matter keeps its form. This is why the objects in your life do not dissolve or reshape themselves at random. Every atom within them is a carefully balanced symphony of fields, each playing its harmonious role. The nucleus shapes the surrounding electron field. The electron field stabilizes the atom's size. The Higgs field gives everything the consistency needed to resist motion. Together they build a universe where structure can endure. If you picture an atom now, try imagining not a cluster of small particles, but a delicate arrangement of field shapes, a glowing center surrounded by soft, layered clouds of vibration. Each cloud holds steady, not through force, but through harmony. The atom becomes a tiny sanctuary of order floating within the vast, ever-present fields of the cosmos. And with that understanding, the simplest unit of matter transforms from a mysterious miniature into a quiet, elegant collaboration. A collaboration that has been unfolding since the earliest moments of the universe, building structure from harmony and weaving the foundations of everything you have ever known. When atoms come close to one another, something quietly elegant begins to unfold. The electron field patterns that surround each nucleus do not behave like rigid shells or protective walls. They are soft, cloud-like regions formed from standing vibrations, and when two atoms approach, these patterns begin to overlap. The overlap is not a collision. It is more like the gentle meeting of two ripples on a pond, creating a new pattern where the waves blend and find a shared rhythm. This new shared pattern is what we call a chemical bond. A bond is not a physical link or a tiny bar connecting two atoms like pieces of a construction set. It is a stable arrangement of vibrations in the electron field, a shared pattern that satisfies the structure of both atoms at once. When this shared vibration lowers the overall energy of the system, the atoms prefer it. They settle into that arrangement as naturally as a musical chord settles into harmony. The result is a molecule, a quiet collaboration between atoms held together not by forceful tethers, but by the shared rhythm of their fields. Imagine two people humming softly in an empty room. At first, each person hums their own note, but if they listen closely to one another, they may find a single pitch that complements them both, a tone that feels more comfortable and stable than the two separate notes. When they hum that shared tone together, the room fills with a unified resonance. A molecular bond behaves with that same spirit. Each atom has its preferred vibrational patterns, but when they find a shared pattern that works better than their isolated states, they remain together in that configuration. These shared vibrational modes give molecules their shapes. Some patterns encourage atoms to settle side by side, others into triangles or chains or rings. The electron field does not place atoms in these shapes like beads on a wire. Instead, the geometry emerges naturally from the stability of the shared field patterns. A straight line forms when that arrangement offers the smoothest, calmest vibration. A bent shape forms when that is the configuration that minimizes tension. Rings arise when a looping pattern fits the field's allowed modes. Molecules become small sculptures crafted by harmony rather than by mechanical design. Once molecules form, the world gains an extraordinary variety of structures. The texture of wood, the flexibility of rubber, the transparency of glass, the scent of a flower, the warmth of a flame. These familiar sensations all arise from the ways molecules interact through fields. The electron field patterns determine how tightly atoms bind, how they arrange themselves, how they respond to heat, and how they reflect or absorb light. Every tangible feature of matter emerges from these invisible harmonies. Take something as simple as colour. When light passes by a molecule, the electron field surrounding that molecule may vibrate in response. Different molecular patterns resonate with different vibrations of light. Some vibrations are absorbed, others pass through or bounce away. The ones that reach your eyes create the colors you see. A leaf appears green not because it contains green paint, but because the electron field patterns in the leaf absorb reds and blues more readily, allowing the green vibrations to reflect back to you. Even the scent of something as delicate as a rose arises from molecular geometry. When a molecule reaches your nose, it fits into a receptor like a key finding the right lock. The shape of the molecule, determined entirely by the shared electron field vibrations that hold it together, tells your body what scent to perceive. A slight change in that shape can lead to an entirely different aroma. One shared field pattern may smell sweet, while another smells sharp or earthy. The nose is exquisitely sensitive to the subtleties of molecular structure. Warmth, too, becomes easier to understand in this picture. When you warm your hands near a mug of tea, the heat you feel is the motion of molecules within the mug, transferring energy to the molecules in the air and eventually to you. That motion is not random jostling in a mechanical sense. It is the electron field patterns shifting slightly, vibrating a bit more vigorously, and sharing their restless energy through gentle interactions. Heat is the field stirring itself at a slightly livelier pace. Flexibility and hardness also emerge from field patterns. A flexible material has molecules arranged in a way that lets their shared vibrations shift easily. The field patterns can twist or stretch without losing stability. A hard material has molecules locked into shapes that resist change. Their patterns allow very little movement before the structure pushes back. This is why rubber bends but diamond does not. Both are made of atoms and fields, but the allowed vibrational shapes of their molecules differ dramatically. If you look around your room right now, every object you see is built from molecules, and every molecule is held together by shared vibrations in the electron field. The fabric of your clothes, the smoothness of a tabletop, the softness of a pillow, even the cool sensation of a metal spoon. All of these arise from the interplay of atomic field patterns. The solidity you feel when you touch an object is a reminder that the electrons within it refuse to shift from their stable shapes. You're not touching matter in a mechanical sense. You're touching a region of space where the electron field has settled into a configuration that resists further compression. This perspective brings the invisible world incredibly close. It reveals that the everyday experience of texture is the feel of field patterns resisting your hand. The shine of polished metal is the way its electron field reflects light. The warmth of skin is the transfer of vibrational energy between fields. The softness of wool is the result of flexible, tangled molecules held together with gentle shared modes. Everything familiar becomes an expression of harmony within the quantum fields that fill space. When you picture molecules now, imagine clusters of atoms held together by gentle rhythms, each one contributing its own vibration to the group. Imagine electron field patterns weaving into one another until they find shapes that feel steady and natural. Imagine the world not as a collection of objects glued together, but as a vast tapestry of shared vibrations, each thread representing a field settling into the form that carries the least tension. And then imagine standing back and seeing the entire universe as a place where matter emerges from these patterns. Tiny islands of stability rising from a sea of fields. From the delicate symmetry of a snowflake to the sturdy beam of a wooden table, from the shimmer of a soap bubble to the structure of your own body, everything is built from the same quiet principles. Fields find harmony with fields, and from that harmony, the richness of the material world unfolds. Through this lens, even the simplest object becomes a marvel. A single stone becomes a mosaic of shared vibrations. A glass of water becomes a dance of shifting molecular patterns, and your own hand, resting gently at your side, becomes a temporary arrangement of fields, stable enough to touch the world, yet soft enough to change and renew itself constantly. The invisible becomes intimate, the abstract becomes familiar, and matter becomes not something mysterious or mechanical, but a gentle, ongoing collaboration between the fields that fill all of space. Energy is one of those words that appears everywhere in science, yet it can feel strangely abstract. You hear about energy in food, energy in storms, energy in electricity, and energy in the quiet warmth of your hands. But beneath all these familiar sensations lies a deeper, more gentle truth. In the language of fields, energy is simply a measure of how disturbed a field is. It tells you how far the field has been pushed from its calmest, most restful state. The more agitated the field becomes, the more energy it carries. The quieter it becomes, the closer it moves toward its ground state, the lowest energy condition it naturally prefers. A helpful way to picture this is to imagine a vast ocean at dawn. When the water is perfectly still, it lies in its ground state. Nothing is stirring it, nothing is agitating it. But if a breeze sweeps across the surface or a pebble falls in, ripples appear. The ocean becomes disturbed. Those ripples carry energy, and the more vigorous they are, the more energy they contain. When the breeze fades or the ripples reach the shore, the ocean slowly returns to stillness, settling back into its lowest energy state. Fields behave in much the same way. Their ground state is the calm configuration they occupy when nothing is disturbing them. Any ripple, any vibration, any shift in their pattern represents energy. A gentle vibration might be a small excitation. A stronger one might correspond to a particle moving quickly, or a field being stirred intensely. The concept becomes surprisingly simple once you see energy not as a substance, but as the level of motion or change within a field. This idea becomes especially clear when thinking about excited states and ground states in atoms. Earlier, the electron field around a nucleus was described as forming standing patterns, each one a stable vibrational mode. These patterns are not equal in energy. The simplest, smoothest pattern is the ground state, the lowest energy configuration the field can adopt around that nucleus. More elaborate patterns, with additional nodal shapes or more complex geometry, correspond to excited states. These states are like higher notes in a musical scale. They require more effort from the field, and that effort shows up as additional energy. Imagine plucking a guitar string very gently. It vibrates with a soft, low tone. That tone is like the ground state of the string, the simplest vibration it naturally adopts. Now imagine plucking it with more intensity or touching it lightly at certain points. You create higher harmonics, each one a more complex pattern of vibration, each one carrying more tension and effort. These are the string's excited states. Fields behave with the same quiet logic. A ground state is calm. An excited state carries more energy because the field must maintain a more elaborate pattern. When an electron field shifts from an excited pattern back down to its calmer, simpler mode, that difference in energy has to go somewhere. It is released as a small packet of light, the tiniest ripple in the electromagnetic field. This is why heated materials glow, why flames emit colors, and why atoms give off light when they settle into lower energy configurations. Energy, in this sense, is the field letting go of its extra tension and relaxing into a more comfortable shape. Heat is another way in which energy appears. When you warm your hands, the molecules in your skin begin vibrating more vigorously. Those molecular vibrations come from the electron field, proton patterns, and quark fields being stirred more actively. The warmth you feel is the sensation of fields carrying extra motion, moving above their calmest state. When something cools, its fields slow down, releasing their excess energy into the surroundings until they return to a more restful configuration. Light, too, is an expression of field energy. A bright beam contains ripples in the electromagnetic field that are vibrating more intensely. A dim light carries smaller ripples. The energy of these ripples determines how strongly the field is disturbed and how it interacts with the world. When you shine a flashlight on a wall, you're sending tiny field disturbances outward, each one carrying a bit of energy that is eventually absorbed by the wall, warming it ever so slightly. The world exchanges energy constantly, in countless small ways, as fields respond to their surroundings. Even motion can be understood through this lens. When a particle speeds up, the disturbance in its field carries more energy. When it slows down, that disturbance settles. The language of motion and the language of energy become the same, both describing how far a field is from its ground state. This view strips away some of the mystery and leaves behind a concept that feels intuitive and gentle. Energy is simply the field's level of restlessness. This idea also helps explain why fields naturally seek their calmest, lowest energy condition. Just as a stretched rubber band will relax when released, a disturbed field tends to move towards stillness whenever possible. It emits light, transfers heat, or rearranges matter in whatever way will reduce its agitation. Eventually, if left undisturbed, a field will settle into its ground state. This settling process is responsible for an enormous range of natural phenomena. Hot tea cools because its fields are losing energy. Excited atoms release light because they are dropping back down to calmer states. Warm objects transfer heat to cooler ones until both share a more uniform, restful condition. Energy, then, is the quiet currency fields use to express change. It flows from one place to another, carried by ripples, vibrations, and rearrangements. It cannot vanish, but it can transform endlessly, shifting between forms as fields respond to their environment. A disturbance in one field can ripple into another. A vibrating molecule can transfer its energy to a neighbor. A photon can be absorbed and give its energy to the electron field. These exchanges create the dynamic tapestry of nature, with each field adjusting its level of restlessness through interactions. There is something calming about seeing energy this way. Instead of imagining it as a mysterious and invisible commodity, you can think of it as the mood of the fields that fill space. Sometimes they are tranquil, sometimes they are slightly stirred, sometimes they are lively and bright, but always they behave according to their structure, seeking harmony and stability wherever possible. And perhaps most comforting of all is the fact that energy moves gracefully. It never appears abruptly without cause. It never disappears without leaving traces. It flows like water, shifts like wind, and settles like ripples returning to stillness on a pond. It is the universe's way of recording what has happened, carrying the imprint of change from one moment to the next. When you look at the world through this view, energy becomes less of an enigma and more of a quiet, reliable companion. It is the measure of how much the universe's fields are stirred at any given moment. It is the rhythm beneath warmth, the glow behind light, and the gently falling transitions that let atoms sigh back into their calmer states. Energy is not a thing, it is a condition, the quiet language through which fields whisper their stories. In the earliest moments of the universe, long before stars existed, long before atoms formed, long before anything resembled the quiet order we see today, the cosmos was a place of astonishing intensity. Every field that now fills space was present, but none of them behaved with the calm stability they display in the modern era. Instead, they were wildly excited, tangled together in a dense hot mixture that pulsed with restless motion. If you could have witnessed this early universe, you would not have seen scattered galaxies or drifting clouds of gas. You would have seen a storm of fields vibrating with such vigour that no structure could possibly survive. This was the universe in its youth, a time when fields refused to settle into their familiar patterns. Temperatures were unimaginably high, so high that every field was pushed far from its ground state. Disturbances rushed through space like waves colliding in a stormy sea. Ripples in one field constantly fed into others, creating a tangled network of motion. Nothing stayed still. Nothing stayed separate. It was a cosmic orchestra, with every instrument playing at once, but without rhythm, harmony, or pause. As the universe expanded, however, something gentle and transformative began to happen. With expansion came cooling. The fields slowly lost some of their agitation, like a pot of water taken off a flame. Their violent vibrations softened. Their interactions became less frantic. Gradually, each field began to recognize its own identity, to behave in ways closer to its modern self. It was as though the universe, in cooling, allowed the fields to introduce themselves properly after a long period of chaotic shouting. In those early moments, the differences between fields were blurred. The electromagnetic field, the strong field, the weak field, and even the Higgs field were all intertwined. They could not settle into the distinct roles they play now. But as temperatures dropped, the universe transitioned through several quiet phases of separation. Each field began to calm enough to maintain its own structure, its own behavior, its own identity. This process did not happen abruptly. It was more like colours gradually separating in water after being stirred together. Slowly, gently, the fields became the distinct players in the cosmic story. When the Higgs field settled into its uniform state, it gave mass to many of the ripples that existed at the time. Before that moment, mass as we know it did not exist. Particles moved with the freedom that would seem strange to us now, gliding through space with little resistance. But once the Higgs field reached its stable value everywhere, the universe changed. Particles began to slow, to develop identity, to interact with one another in new ways. It was one of the most significant transitions in cosmic history, a quiet but profound shift. As cooling continued, the strong field began to behave in the way it does today, confining quarks into stable proton and neutron patterns. Before that, quarks moved more freely, unable to settle into the tightly bound structures that now form the cores of atoms. When confinement set in, the quark fields created the first stable building blocks of matter. These patterns were tiny islands of structure, forming in a universe that was slowly learning the meaning of order. Yet the most poetic aspect of this early era lies in the tiny fluctuations that existed in the fields. Even in the primordial chaos, fields were not perfectly uniform. There were small variations, tiny differences in energy from point to point, gentle irregularities that would have gone unnoticed at the time. These variations were slight, no more significant than the faintest ripple on an otherwise calm pond. But the universe has a remarkable habit of amplifying the subtle. As space continued to expand, these small fluctuations grew. Regions where the field had a slightly higher energy density pulled in more matter. Regions with slightly lower density expanded more quickly. Over vast periods, these small differences created the seeds of structure. The first galaxies, the first stars, the first cosmic clusters, all can trace their origins back to these gentle early ripples in the fields. Imagine sprinkling fine sand on a drum and tapping it softly. Tiny patterns form without any intention, guided only by the drum's natural vibrations. In the same way, the early fields created patterns across the cosmos. These patterns became the scaffolding upon which all later structure was built. It is one of the great cosmic ironies that the enormous beauty of the night sky owes its existence to microscopic fluctuations frozen into place during a time when nothing remotely resembling a star yet existed. As the universe cooled further, the fields that once behaved like a tangled storm began to form a layered cooperative structure. Heat dissipated. Disturbances calmed. The universe transitioned from wild, unrestrained motion into a quieter, more stable environment. The fields found their preferred states, their harmonious configurations. In this calmer space, particles could behave consistently. They could combine, settle, and eventually begin forming the first simple atoms. Space changed from a chaotic ocean of vibrations into a vast, expanding stage upon which the drama of matter could unfold. The shift from confusion to order is one of the most beautiful stories in physics. It is the story of the universe learning to breathe more slowly. It is the story of fields discovering balance. It is the story of a cosmos that began in a state of intense, unstructured energy and gradually softened into something capable of complexity, structure, and eventually life. If you were to watch the evolution of the early universe as a time-lapse, you would see the fields gradually quieting, like a storm slowly losing its fury. First, the violent ripples would dominate everything. Then the storm would ease and gentle fluctuations would take their place. Finally, vast regions of calm would appear, stable and smooth, with only small ripples left to guide the future shape of galaxies. The modern universe, with its spiral galaxies, glowing stars, drifting nebulae, and swirling clusters, carries the imprint of that early dance of fields. Every atom in your body traces its lineage back to a time when the universe was far too hot for atoms to exist. Every molecule in your surroundings grew from seeds planted in those earliest fluctuations, and through it all the fields have remained. They have cooled, calmed, settled, and stabilized, but they are still here, woven into every corner of the cosmos. The difference is simply that they have aged. They have matured from their wild youth into the quiet, reliable foundations of the universe we experience today. The early universe was not a place of emptiness or silence. It was a place of overwhelming energy, of restless fields learning how to become the architecture of reality. And in that transition from chaos to calm, the cosmos found its path towards structure, a path that ultimately leads to everything we know, everything we see, and everything we are. If you spend a moment looking around your surroundings, you might notice a quiet sense of order in the world. A leaf often mirrors itself along a central line. A snowflake repeats intricate patterns with gentle precision. A seashell spirals in a way that feels both natural and inevitable. These examples are not coincidences. They reflect a deeper principle woven through nature: symmetry. In the language of fields, symmetry is not simply a pleasing aesthetic. It is a powerful blueprint, a set of hidden rules that guide how the universe behaves. At its heart, symmetry means that something remains unchanged when transformed. You can rotate a circle, and it still looks the same. You can reflect a butterfly's wing along its center and recognize its outline. You can slide a repeating pattern across a tiled floor and see no difference in the design. These simple ideas might seem far removed from the world of quantum fields, yet they form the backbone of how fields behave. Every field in the universe obeys certain symmetries. These symmetries dictate how the field can move, how it can vibrate, and how it can interact with other fields. They are like quiet instructions written into the fabric of reality, always present, always followed, yet rarely noticed. When a field remains unchanged under a transformation, a rotation, a reflection, or a shift in position, it carries a particular symmetry. And when a symmetry exists, something profound emerges, a conservation law. Nature rewards symmetry with consistency. Consider the simplest form of symmetry, translation. If you slide a pattern across a floor and it stays the same, the pattern has translational symmetry. In physics, translational symmetry means that the laws of nature are the same everywhere. A ripple in a field behaves the same on your desk as it would deep in a distant galaxy. Because this symmetry holds, one of the universe's most fundamental rules arises, the conservation of momentum. Nothing in nature gains or loses momentum without an interaction, because the laws of physics do not change from place to place. Next, imagine rotation. If you rotate a perfect sphere, nothing about it changes. This symmetry, when applied to fields, means that the laws of nature do not depend on the direction you are facing. There is no privileged orientation in space. Because of this symmetry, angular momentum is conserved. A spinning planet will keep spinning unless acted upon. A twirling figure skater retains their graceful motion. The symmetry of direction underlies the stability of rotation throughout the cosmos. Reflection symmetry, or mirror symmetry, offers another layer of meaning. If you reflect a pattern and it remains unchanged, the pattern exhibits mirror symmetry. For fields, this principle can be more subtle. Some fields obey mirror symmetry, some gently break it. Yet the presence or absence of this symmetry shapes the behavior of particles in ways that influence the structure of matter itself. Even when mirror symmetry fails, the breaking of that symmetry becomes a source of insight into how the fields are arranged. These simple symmetries, translation, rotation, reflection, are easy to picture, but the universe holds deeper and more abstract versions as well. They are not as straightforward as rotating an object or sliding a tile, but they function in the same way. They define what remains unchanged when a field transforms. These hidden symmetries guide how particles appear, how they behave, and how the forces between them operate. They create patterns in the behavior of fields that would otherwise seem inexplicable. Take the electron field, for instance. Its symmetry ensures that every electron in the universe behaves in the same way, no matter where or when it appears. Without that symmetry, electrons could come in countless varieties, and atoms would fail to form the consistent structures needed for matter. Or consider the strong field. Its symmetries dictate how quarks combine into stable patterns, ensuring that protons and neutrons emerge with reliable properties. Symmetry keeps the universe from being chaotic or unpredictable. One of the most beautiful aspects of symmetry is how quietly it works. You might assume that the complexity of nature comes from complicated underlying rules, but often the opposite is true. Complexity arises from simple, consistent symmetries repeated across scale. Snowflakes, crystals, spiral galaxies, and even the behavior of fields all follow patterns shaped by symmetry. These patterns give rise to the structure of matter, the flow of energy, and the organization of the cosmos. Even conservation laws, rules that feel so fundamental that they seem almost philosophical, are simply reflections of symmetry. The conservation of energy arises from the symmetry of time. If the laws of physics do not change from one moment to the next, then energy must be conserved. It cannot appear or disappear suddenly any more than a melody can introduce a note that does not belong. This symmetry creates a sense of continuity, a reassurance that the universe remains stable across every passing second. You can imagine symmetry as the quiet architect behind everything. It does not impose structure harshly. It does not dictate behavior with rigid demands. Instead, it offers a set of guidelines, and the fields follow those guidelines effortlessly. When a field vibrates, it does so in ways allowed by its symmetries. When a particle appears, its properties reflect the symmetries of the field it emerges from. When matter forms, the arrangements that last are those that honor the underlying patterns. There is contemplative beauty in knowing that the universe builds itself from these quiet instructions. You might stand beneath a starlit sky and feel that the world is full of intricacy and wonder, and you would be right. But beneath that intricacy lies a deep simplicity, a handful of symmetries, patiently guiding fields as they weave together into the complex tapestry of existence. Symmetry does not remove creativity from nature. Instead, it makes creativity possible. By providing stable patterns, it allows complexity to grow without collapsing into confusion. It gives the universe a framework upon which to build stars, galaxies, atoms, and life. Without symmetry, the world would be a restless, unpredictable place. With it, the universe becomes a place where order and beauty emerge naturally. When you think of symmetry in nature, let your mind drift beyond the shapes you can see to the patterns you cannot. Imagine the fields filling space, vibrating and flowing with a grace that mirrors the quiet logic of symmetry. Imagine the universe honoring these hidden blueprints in every motion, every interaction, every ripple of energy. And then imagine how extraordinary it is that something so simple, something that asks only for consistency, can shape a cosmos as rich and varied as ours. Symmetry is the universe's way of being elegant, a quiet principle that holds everything together without ever asking for attention. Space and time form the quiet stage on which the entire universe unfolds. They hold the galaxies in their vast embrace, carry starlight across immeasurable distances, and allow every particle and ripple to move, dance, and evolve. Yet this stage is not an empty backdrop. It is shaped, supported, and subtly sculpted by the very fields that inhabit it. Without fields, space would have no structure. Without fields, time would lose its rhythm. The universe would lose the fabric that gives everything a place to exist. You can imagine space-time as a calm, stretching fabric, not a fabric woven from threads, but something more abstract, a smooth, continuous expanse that bends, stretches, and curves without tearing. This fabric responds to what happens within it. A massive star resting in space gently reshapes the geometry around it. A planet orbiting that star follows the curved path created by this reshaping. Nothing pushes the planet directly. The planet simply moves along the contours of the fabric beneath it. Gravity, in this view, becomes the quiet conversation between matter and the geometry of space-time. But fields do not merely sit on this fabric, waiting to be influenced. They help define the fabric itself. Every field, from the electromagnetic to the electron field to the Higgs field, exists everywhere in space, and their presence provides structure to the otherwise featureless void. Each field assigns values to every point in the universe, marking space with the gentle texture that allows positions to have meaning. Even the vacuum, with its subtle fluctuations, helps give space the stability and uniformity we rely on when we speak of distance or direction. In a sense, fields and spacetime support one another. Fields need spacetime to exist, to vibrate, to spread their ripples. Spacetime needs fields to fill it, to lend it structure and definition. If you removed all fields, even the quietest ones, the stage itself would unravel into something that no longer resembles the space we know. Without fields, the idea of distance would lose its footing, and time would cease to move in a steady rhythm. The universe would be left without the scaffolding that allows anything at all to take place. To picture the relationship between fields and spacetime, imagine stretching a sheet of gentle fabric across a frame. The fabric is smooth, but its tension and behavior depend entirely on what fills the space beneath and around it. If you place a small weight in the center, the fabric slopes slightly. If you remove the weight, the fabric returns to its even shape. Fields are like the unseen forces beneath the fabric, controlling its tension, ensuring it stays smooth, and giving it the ability to respond to what rests upon it. The gravitational field is the most direct example of how geometry and fields intertwine. This field describes how matter and energy influence the shape of spacetime. When a massive object sits in space, it changes the gravitational field around it, and this change informs spacetime how to curve. Light bends around stars not because something physically pushes it, but because the geometry it travels through has gently shifted. The light is simply tracing the curves of the fabric, following the easiest path available. Even time is shaped by this interplay. A strong gravitational field slows the passage of time compared with regions where gravity is weaker. Time becomes a flexible dimension, stretching and compressing based on the geometry shaped by fields. A clock placed near a massive planet ticks slightly more slowly than one far from any significant gravitational influence. This slowing is not a trick or illusion. It is the fabric of time responding to the contours of space-time itself. And yet, despite these profound effects, the experience of space-time is overwhelmingly calm. You do not feel yourself moving through a curved fabric or drifting along field-shaped paths. The contours are gentle, especially on human scales. The ground beneath you feels stable. The flow of time feels regular. The universe has arranged its underlying structures so that complexity can grow on a foundation of quiet consistency. Other fields contribute their own roles in defining this stability. The Higgs field gives particles mass, and through that mass, they influence the gravitational field. The electromagnetic field provides the behavior that allows atoms to form, and those atoms contribute to the distribution of matter that shapes space-time. The strong and weak fields govern the behavior of nuclei, determining how matter concentrates in stars and planets, and those concentrations feed back into the gravitational field as well. Nothing is isolated. Everything shapes everything else. This interconnection creates an elegant unity. Fields fill space-time. Space-time gives fields a place to exist. Mass shapes geometry. Geometry guides motion. Energy disturbs fields. Fields respond. And from this gentle loop, the universe gains its form. You can think of it as a cosmic handshake, a quiet agreement between geometry and vibration, each one supporting the other in a balanced partnership. If you were to drift through space far from any planet or star, you might feel as though you had entered a peaceful emptiness. Yet even there, the fields would surround you, steady and uniform, giving space its shape. Space-time would be smooth and straight, like an undisturbed sheet, because nothing nearby would be bending it. But if you watched a star from afar, you would see light curve around it gracefully. You would see planets follow elegant arcs. You would witness the fabric of space expressing the presence of fields and matter. On much larger scales, the geometry of space-time becomes the stage for cosmic evolution. Galaxies follow the curves carved by enormous clusters of matter. Waves of gravitational disturbance ripple outward from dramatic events, like stars merging or black holes colliding. These waves are not vibrations in a material medium. They are vibrations in space-time itself, gentle undulations of the cosmic fabric carrying information across the universe. All the while, the fields remain present, shaping the fabric as softly as wind shapes dunes. Their presence keeps space-time from collapsing into disorder or slipping into undefined emptiness. They give the cosmos its backbone, its stability, and its capacity to unfold with coherence through billions of years. Understanding this relationship brings a powerful sense of awe. Space is not a void. Time is not an invisible metronome. Together they form a living stage, one shaped by the activity of fields and shaped in turn by the matter that those fields allow to exist. Every moment you experience, every movement you make, unfolds within this delicate geometry. You're carried through life on a fabric shaped by stars, by galaxies, by the quiet breath of fields that fill every inch of the universe. And even though the dance of space-time is subtle, too soft to feel directly, it is always there, guiding the paths of planets, the drift of light, and the winding journey of the cosmos itself. Quantum fields may feel distant, abstract, or impossibly tiny, but they are woven into your everyday life in ways that are surprisingly practical. Every time you switch on a light, make a phone call, scroll through a screen, or even receive medical care, you're relying on the precise behavior of fields you cannot see. In a sense, modern technology is just humanity learning how to coax these fields into performing useful tasks. Once you recognize this, the invisible world becomes intimately familiar, as comforting as a warm lamp on a quiet evening. Begin with something simple, a laptop or a smartphone. These devices rely entirely on the electron field. When a current flows through a wire or chip, nothing small and solid is marching along the metal. Instead, the electron field is being gently reshaped. Tiny disturbances move through it, creating patterns that engineers can guide and control. By arranging materials in just the right way, we produce regions where the electron field prefers to vibrate in one pattern rather than another. When those patterns shift, information is encoded. Every message typed, every image displayed, every video watched comes from subtle adjustments in the ripples of the electron field as it moves through a complex lattice of atoms. Semiconductors, the heart of modern electronics, make this guidance possible. They are materials in which the electron field finds certain vibrational patterns blocked and others allowed. By introducing tiny impurities or layering materials carefully, we can shape the electron field's behavior with extraordinary precision. The result is the transistor, a device that can turn electron field vibrations on or off in a controlled way. It is a simple idea with profound consequences. By linking billions of these switching elements together, we create circuits capable of processing information, rendering pictures, running simulations, and even guiding spacecraft. Even something as ordinary as a laser pointer or the scanner at a supermarket checkout is a direct expression of organized electromagnetic field vibrations. A laser is simply the electromagnetic field persuaded to vibrate in a perfectly coordinated way. Instead of many random ripples traveling in all directions, a laser produces a single, smooth ripple, moving forward with remarkable purity. This is why laser light is so consistent, so bright, and so sharply defined. It is the electromagnetic field in its most disciplined state, like a choir singing a single note in perfect harmony. Medical imaging also depends on fields in ways that feel almost magical. Magnetic resonance imaging, for example, uses the interaction between magnetic fields and the tiny ripples in the fields inside your body. When placed within a strong magnetic environment, particles in your tissues align their internal vibrations in specific ways. By sending gentle pulses of energy and listening to how the fields respond, the machine creates detailed images of organs, muscles, and even the brain. Nothing is touched or cut. The imaging works because fields communicate quietly with one another, revealing information through their subtle responses. Another example lies in quantum sensors, a rapidly growing area of technology that uses the exquisite sensitivity of fields to detect tiny changes in the world. These sensors can measure faint magnetic variations, slight differences in gravity, or even delicate shifts in time. They rely on the fact that quantum fields respond to their environment with extraordinary precision. A small change in temperature, pressure, or geometry can alter the vibrational patterns in a field, and by measuring those changes we learn something about the world around us. These sensors help guide aircraft, monitor Earth's atmosphere, and support advanced medical research. Even the simple electric light in a room depends on field behavior. When current flows through a bulb, the electron field interacts with the atomic structure of the filament or the gas inside. This interaction disturbs the electromagnetic field in such a way that light is produced. The color of the light, the warmth it gives off, and the efficiency of the bulb all depend on the details of how the electron field and electromagnetic field exchange energy. A soft, warm glow is nothing more than a gentle shower of electromagnetic ripples created by the settling vibrations in matter. Wireless communication also rests entirely on fields. When you make a phone call or send a message, your device creates ripples in the electromagnetic field. These ripples spread out across space, carrying patterns that represent information. Other devices detect these patterns and interpret them back into sound, text, or images. No wires are needed. The electromagnetic field is the medium, a silent ocean capable of carrying signals around the world and beyond. Even satellites high above the Earth rely on the stability of this field, sending and receiving whispers of electromagnetic motion across enormous distances. The global positioning system, which guides everything from phone navigation to aircraft, depends on the field of time itself. Each satellite carries extremely precise clocks, and spacetime's gentle curvature affects the rate at which these clocks tick. The satellites broadcast their timing signals, and receivers on Earth compare them to determine position. It is a quiet reminder that quantum fields, the Higgs field, and spacetime geometry form the mathematical heartbeat of navigation. Refrigerators, too, make use of quantum fields in ways that feel perfectly ordinary. Magnetic fields generated by coils inside help regulate the flow of electrons and heat within the system. Even everyday magnets on the door rely on the quantum alignment of electron field patterns within a material, giving rise to the familiar pull that lets the magnets cling to the metal. When you charge a battery, chemical reactions inside shift the configuration of electron field patterns in molecules. These shifts release or store energy by changing the vibrations within the fields. Plugging your device into a wall socket simply invites those rearranged field patterns to migrate back into motion. A battery is, in essence, a container for structured energy stored inside molecular field patterns, waiting to be released into circuits. Even the humble toaster becomes a celebration of quantum field behavior. Heat in the toaster coils is nothing more than increased motion in the electron field and atomic lattice. When the coils glow, you are seeing the electromagnetic field responding to that motion and radiating light. The golden toast you enjoy in the morning is the result of chemical bonds in bread breaking and reforming, driven by the energy carried through these vibrating fields. The more you look, the more it becomes clear that the modern world, with its screens, lights, sensors, engines, medicines, and communications, is built not on magic, but on the calm, predictable behavior of fields. Their interactions may be invisible, but they are practical and familiar. They allow the world to function in ways we often take for granted. Quantum fields are not distant concepts hidden away in laboratories or buried in dense textbooks. They are present in every device you touch, every bit of information you send, every beam of light you see. They shape how materials behave, how energy flows, and how technology operates. By learning to understand and guide them, humanity has woven the abstract into the everyday. And in recognizing this, the invisible world begins to feel less mysterious. The fields that fill space are the same fields that light your room, power your phone, scan your body in a hospital, and carry your voice across great distances. They are practical, reliable companions, quietly supporting the rhythm of ordinary life. When you trace the story of modern physics from its earliest ideas to its most precise discoveries, you find that each step brings you closer to a quiet, elegant conclusion. Quantum fields appear to be the deepest layer of reality we currently understand. They form the framework that explains not only the behavior of what we call particles, but also the forces that move them, the structure of matter, the nature of light, and even the shape of space-time itself. And remarkably, once this framework is in place, many of the contradictions that puzzled earlier generations simply fall away. The journey to this understanding begins with unification. For a long time, particles and forces were viewed as separate things. Particles as tiny objects with specific properties, and forces as invisible influences acting upon them. But as the field model developed, something surprising happened. The distinction began to fade. Each particle turned out to be a ripple, a stable vibrational pattern in an underlying field, and each force arose from the way fields interact with one another. Instead of separate ingredients, particles and forces became different expressions of the same underlying entities. The electromagnetic field produces photons as its ripples. The electron field produces electrons. The quark fields give rise to the internal building blocks of matter. Even the Higgs field creates the conditions that give mass to many of the excitations in other fields. The strong and weak fields produce their own characteristic ripples, organizing everything from nuclear stability to radioactive decay. Each field describes a family of excitations, and the interactions between fields explain the relationships between these families. This unified picture became powerful not because it was aesthetically pleasing, though it certainly is, but because it worked with astonishing accuracy. Experiments repeatedly confirmed predictions that emerged from the field model. Subtle details of particle behavior, intricate patterns in particle collisions, rare transitions between excited states, all matched what field theory described long before the experiments were performed. Even the existence of the Higgs field, proposed purely to resolve theoretical inconsistencies, was confirmed decades later by careful observation. Every time the theory was tested, it passed with an almost serene precision. One of the biggest triumphs of the field model is its ability to dissolve contradictions that haunted earlier attempts to understand matter. The wave-particle paradox, which confused scientists for many years, becomes clear once waves and particles are understood as two perspectives on the same phenomenon. The electron behaves like a wave because it is a vibration in a field. It appears particle-like during measurement because the field's energy comes in discrete packets. The contradiction disappears once the underlying field is acknowledged. Similarly, the strange ability of particles to appear and vanish, to tunnel through barriers, or to remain in multiple states until measured becomes less mystifying when viewed through fields. A particle is not an object stored somewhere like a marble in a drawer. It is a ripple in a field that can spread, split, combine, or shift depending on the field shape. What once looked like impossible behavior becomes natural once the assumptions of classical particles are replaced by the more fluid behavior of fields. Even the forces between particles, which once required imaginary pushes or pulls acting across space, become simple when viewed as interactions between fields. No invisible hands or mysterious mechanisms are needed. Fields respond to disturbances in each other, reshaping themselves in ways that guide the motion of their ripples. The universe becomes a place of continuous communication rather than abrupt, mechanical events. This ability to remove contradictions is one of the strongest signs that fields lie close to the heart of nature's structure. When a theory makes the world simpler, more coherent, and more predictable, it usually means that it captures something fundamental. The field model does exactly that. It replaces a collection of puzzling and disconnected observations with a single, consistent framework in which everything fits. Another reason quantum fields are considered the deepest layer we know is their remarkable completeness. They do not merely describe a few aspects of nature, they describe all known matter and forces except gravity, and even gravity is likely to have a field-like description at the deepest levels, though the full picture has not yet been worked out. When a framework explains so much with such precision, scientists naturally pay attention. But perhaps the most compelling argument for fields as the foundational layer is that they require no extra scaffolding to stand. In classical physics, particles needed forces to guide them. Forces needed rules to define them. Space needed a container to hold them all. The field model needs none of this. Fields exist throughout space, and their ripples give rise to particles. Their interactions produce forces. Their structure shapes the behavior of energy. Layer by layer, fields explain one another without needing something deeper underneath. Even time and space themselves, which once seemed like rigid backgrounds, become flexible and intertwined with fields. The Higgs field sets the stage for mass. The gravitational field shapes the geometry. The vacuum is a resting state of all fields at once. Each layer reinforces the others. Nothing feels arbitrary. All of this makes quantum fields a powerful and satisfying foundation. But their importance is not only scientific. Understanding fields adds an emotional depth to the story of the universe. It shows that beneath the complexity of matter, beneath the colours and textures and shapes of the world, lies something gentle and unified, a series of continuous fields quietly vibrating, interacting, and finding harmony. The universe becomes a place of patterns rather than pieces, unity rather than fragmentation. This gentle foundation prepares you for the reflective chapters ahead. As the story of quantum fields approaches its conclusion, it becomes clear that these fields do more than explain the behavior of matter. They provide a way of understanding the universe that is both deeply scientific and quietly comforting, a way of seeing the world as connected, coherent, and full of structure at every level. Quantum fields may not be the final answer. Physics is a living science, always evolving, always discovering, but for now they form the deepest and most elegant layer we have found. They explain the universe with clarity and grace, and they offer a reminder that even the most complex phenomena grow from simple foundations, humming gently beneath all things. When you look in a mirror, you may see a familiar face, a set of features you recognize instantly as yourself. But beneath that familiar surface lies something far more delicate and astonishing. You're not a fixed object. You're not made of tiny marbles or static pieces that endure unchanged. Instead, you're a living pattern, a self-maintaining arrangement of quantum fields that has learned how to persist, adapt, and renew itself moment by moment. Every part of you, from the tip of a hair to the thought forming quietly in your mind, is built from fields interacting in stable, repeating ways. Atoms form the scaffolding, molecules perform the chemistry of life, and cells create the architecture that holds everything together. Yet at the deepest level, it is all vibrations, ripples, and standing patterns in fields that fill space. These fields existed long before you were born, and they will remain long after your individual pattern dissolves. For a brief stretch of time, they come together in a configuration that is recognizably you. In this sense, your existence is less like a statue carved from stone, and more like a melody played on an instrument. The melody persists even though no single note defines it. Notes appear, resonate, and fade, yet the pattern remains. Your body behaves in this same dynamic way. Atoms come and go. Molecules are constantly replaced. Even the cells in your organs renew themselves over time. But the pattern, the arrangement that makes you who you are, continues, reshaping itself gently as it moves forward. Another helpful metaphor is a flame. A flame has shape, colour, warmth, and presence, yet there is nothing solid inside it. It persists because fresh fuel enters, energy flows through it, and gases escape. Its identity lies in the ongoing process, not in a permanent piece of matter. You are similar. Every moment of your life, energy is exchanged, matter flows in and out, and yet the pattern holds. This pattern is maintained by the quiet logic of fields that settle into stable forms whenever conditions allow. You might also think of yourself as a flowing current in a river. The water changes constantly, yet the current keeps its character. It bends around rocks, quickens in narrow passages, slows in wide pools, yet it remains recognizably itself. A human being is a current in the river of fields, shaped by experience, environment, memory, and biology, yet preserved by a deeper continuity. There is nothing mystical in this. It is simply the natural consequence of matter being made from fields rather than fixed pieces. If everything is a vibration in a field, then stability comes not from permanence, but from maintenance, from the ability of a pattern to keep renewing itself amidst constant change. Life is the name we give to the patterns that are exceptionally good at doing this. Your cells maintain themselves by drawing on energy stored in molecules. Those molecules come from food, air, and sunlight captured long before you were born. The atoms inside you have passed through countless stars, planets, oceans, and living things. They did not begin with you, and they will not end with you. They are borrowed temporarily by your pattern, and will someday be released back into the greater flow. Yet the pattern you embody right now is unique. It arises from the particular ways your cells organize themselves, the particular shape of your neural pathways, the memories stored in them, and the relationships that enrich your life. Identity then becomes a process rather than a possession. You are the continuity of a pattern woven across time. You are the series of gentle transitions that link childhood to adulthood, one moment to the next. Even though everything within you changes, the thread connecting those changes persists. It is a quiet reassurance that you're not defined by what stays the same, but by the way change itself carries your story forward. This perspective can offer comfort. If you are a pattern in fields, then change is not something that happens to you from the outside. It is something you are built to navigate. You are made from structures that thrive on adjustment. Your brain strengthens connections that are used frequently and allows others to fade. Your body heals, adapts, and renews. Even your emotions evolve, responding to new situations while carrying echoes of past experience. All of this is part of the pattern being itself, flexible, resilient, and continuously unfolding. It also brings a gentle humility. The fields that shape you shape every other living thing as well. Life is a family of patterns, each one unique, each one temporary, each one arising from the same underlying fabric. The boundaries that feel so solid in everyday life soften when viewed through the lens of fields. The same fields that ripple within you ripple within the person sitting next to you, the tree outside your window, and the stars in the night sky. You are distinct, but you're not separate. Your existence is part of a much larger tapestry, woven from the same threads. Far from diminishing individuality, this view can make existence feel even more precious. A melody is meaningful precisely because it flows, changes, and ends. A flame is beautiful precisely because it dances. A river is alive because it moves. Your life, shaped by countless interactions in the fields that fill space, is a pattern that has never existed before and will never exist again in exactly the same way. There's a quiet wonder in knowing that your thoughts, your memories, your presence are all emergent expressions of fields behaving in stable, intricate ways. The fact that such complexity can arise from simple foundations speaks to the extraordinary richness of the universe. From quantum fields that ripple invisibly across space, a pattern capable of contemplating its own existence has emerged, and that pattern is you. Understanding this does not require abandoning the everyday sense of self. You still make decisions, form relationships, and move through the world with intention. But beneath those experiences lies a gentle truth. You are, at every moment, a living arrangement of fields keeping themselves together with remarkable skill. And perhaps that is why this perspective feels deeply reassuring. It dissolves the distance between the abstract and the familiar. It shows that the same fields shaping galaxies also shape your heartbeat. It reveals that your existence is part of the universe's natural tendency to form order from simplicity, and it suggests that even though everything changes, the pattern of your life has coherence, continuity, and meaning. For now and for as long as the fields maintain the harmony of your form, you are a beautiful, sustained vibration in the cosmic fabric, a moment of order in a universe that knows how to create extraordinary patterns. When you take a step back from the details of quantum fields, the ripples, the interactions, the patterns that shape matter and light, a larger picture emerges, one that feels both scientific and quietly poetic. The universe begins to resemble a vast, gentle symphony, played not on instruments of wood or metal, but on the fields that fill every corner of space. Each field contributes its own voice, its own tone, its own rhythm. Some sing with bright, swift vibrations, Others hum with deep, steady resonance. Together they create a layered music that shapes everything from the tiniest atom to the largest galaxy. These vibrations do not exist in isolation. They overlap, blend, and intertwine, creating harmonies that allow the universe to form structure rather than noise. The electron field folds itself into elegant patterns that sustain atoms. The electromagnetic field carries light across unimaginable distances, illuminating worlds that have never met. The strong and weak fields maintain the quiet storm inside nuclei, ensuring that matter has a center sturdy enough to endure. The Higgs field provides the slowing touch that gives mass its meaning, and beneath all of this, the gravitational field curves the stage on which the entire performance unfolds. None of these fields competes with the others. They coexist effortlessly, each playing its part in the cosmic score. If one were removed, the music would fall apart. Without the electron field's steady harmonies, atoms would lose their structure. Without the electromagnetic field's radiant tones, light itself would vanish. Without the Higgs field's quiet presence, nothing would settle or hold its shape. Without the gravitational field's slow, deep drum, the dance of stars and galaxies would lose its choreography. Yet despite their importance, these fields rarely announce themselves. They work in the background, maintaining order with a generosity that asks for no attention. In this way, the universe feels less like a machine and more like a living piece of music, something that flows, adapts and evolves with an understated grace. Each field vibrates according to its own rules, but together they create a world filled with structure and beauty. The harmony becomes even more striking when you consider the delicate balance required for complexity to emerge. A small change in the relative strengths of fields, a slight shift in how they interact, and the universe would unfold in a completely different way. Stars might never ignite, atoms might never hold together, molecules might fail to form patterns, life with all its subtlety might never arise. And yet, here you are, listening to the soft explanation of these fields, built from their vibrations, shaped by their harmonies, and carried by their quiet stability. There is a gentle comfort in knowing that the universe is not chaotic at its core. Beneath every storm, every galaxy, every heartbeat, lies a foundation of calm, pervasive order. The fields that give rise to everything operate with remarkable consistency, maintaining patterns that have endured for billions of years. Galaxies swirl not because they are pushed, but because the gravitational field curves space into a dance. Light travels not because it is thrown, but because the electromagnetic field allows ripples to glide freely. Matter persists not because it is locked together, but because the electron field prefers harmonious shapes that remain stable over time. When you view the universe as a symphony of fields, even the most familiar sights take on new meaning. A candle flame becomes a brief, warm improvisation, a small region where chemical field patterns rearrange themselves into light and heat. A tree becomes a long, slow composition shaped by sunlight, water, and biological rhythms, all of which depend on the reliable behavior of fields. Your own thoughts become patterns of electrical activity in the brain, guided by the same underlying fields that shape stars. This perspective invites you to appreciate the quiet unity underlying everything. No matter where you look, at a distant galaxy glowing softly in the night sky, or at a cup of tea cooling on a table, the same framework supports it all. The fields vibrate, the patterns form, the universe expresses itself. The scale may change, but the principles do not. The cosmic overture that began in the early universe continues now, unfurling in every moment and every place. And the beauty of this symphony is that it does not need a conductor. It plays itself, guided by the intrinsic structure of fields and the symmetries that shape their behavior. Each note arises naturally from what came before. Each ripple finds its place among the others. Even the vast, swirling motions of galaxies emerge from the same principles that organize the quiet vibrations inside an atom. The universe is unified not because it is simple, but because it is coherent. Its layers fit together because they grow from the same foundational patterns. There's something profoundly soothing about understanding this. It suggests that even though reality can appear chaotic, noisy, or unpredictable at times, beneath the surface lies an enduring order. Patterns rise, dissolve, and rise again, but the fields remain steady, offering a kind of cosmic continuity. They do not enforce harmony. They simply allow it to emerge whenever conditions are right. And when you listen closely, not with ears, but with awareness, you might sense that you are part of this vast, quiet music. Your presence is one of its passing melodies, shaped by the interplay of fields that have been vibrating since the dawn of the cosmos. You are woven into the harmony, participating simply by existing. You are one of the universe's quieter notes, subtle yet essential, contributing your own resonance to the unfolding composition. As this journey winds to a close, the details of fields and vibrations soften, leaving behind a gentle sense of connection, not to equations or theories, but to the quiet structure beneath everything. You have travelled through a universe woven from calm, overlapping rhythms, each one supporting the next, each one contributing to the world you move through every day. And perhaps, in following those threads, something has settled inside you as well, a sense that reality, even in its complexity, rests on foundations that are steady, elegant, and deeply peaceful. What began as an exploration of strange ideas has unfolded into something more intimate. The universe no longer feels like a distant expanse of cold machinery. It feels like a place shaped by harmony, by patterns that form naturally, by fields that settle into quiet order whenever they can. Even the wildest moments of creation eventually softened into structure. Even the smallest disturbances found their place in the larger rhythm. There is comfort in knowing that beneath everything, beneath matter, beneath movement, beneath life itself, lies a gentle logic that keeps the world coherent. And through that lens, your own existence becomes part of that quiet structure. You're made from the same fields that shape galaxies, the same vibrations that fill space, the same subtle patterns that make atoms possible. Your thoughts, your breath, the quiet beat of your heart, all arise from a universe that has spent billions of years learning how to form stable, intricate patterns. You are one of those patterns, temporary, beautiful, and held together by the same calm principles that guide the stars. There is soothing reassurance in recognizing that nothing about you is separate from the rest of the cosmos. The same harmony that shapes distant starlight shapes your presence here, in this moment. You belong to the universe in the most literal way, made from its fields, carried by its rhythms, supported by its quiet structure. And in understanding that, you may feel a softness settle around you, as though the vastness of everything has become just a little more familiar. If you've listened through these ideas while winding down for the night, perhaps you can feel the mind beginning to quiet. Thoughts drift more slowly, the breath deepens, the body settles. Just as fields seek their calmest states whenever they can, you too are allowed to soften into rest. The day has carried its share of motion and noise, but now the rhythm changes. Now you can move towards stillness. Let yourself sink gently into that feeling. There's nothing left to solve, nothing left to understand, nothing left to hold. The universe itself is built on patterns that settle naturally, and you can follow that same path. Like a field releasing its excess energy, you can let the mind fall toward its quietest shape. A peaceful state, a resting state, a state where thoughts become distant like ripples smoothing out on a pond at dusk. As the mind loosens its grip, the world softens. The room grows quieter, the breath becomes slower, and the universe continues its quiet symphony around you, steady and unchanged, carrying you gently within it. You are part of that music, and the music does not need your effort to continue. It plays whether you are awake or drifting, thinking or dreaming. So allow yourself to drift. Allow the story to fade into the background. Allow the steady rhythm of your own breath to guide you toward rest. Thank you for spending this time here, exploring these gentle ideas and letting them unfold at their own pace. It has been a quiet journey through the hidden structure of everything, from the smallest ripples to the vastness of the cosmos, and your presence has been part of that journey's meaning. Now, as the day settles behind you, you can let the universe hold the weight of things for a while. There is nothing you need to do, nothing you need to fix. You can simply rest in the knowledge that the same calm foundations that shape reality will still be there when you wake. May your night be peaceful, your dreams soft, and your sleep deep. And when morning comes, the quiet harmony of the universe will greet you again, just as steady, just as gentle, waiting to carry you forward into whatever comes next.